composed of registers and stack, and one must be included into another. And here I just had like basically type inclusion and range inclusion with a simple example, but there are like more stuff actually that is checked nowadays. But to give you a glimpse, you can see you have like a current state on the left. Two registers in these states, very simple states, any scalar for R0 and the scalar 0 for R1. And the state that you saved in a previous exploration contains R0 with initialized registers and R1 with a scalar from 0 to 10. So you can see for R0, you have like type inclusion, scalar, any scalar is included in like uninitialized registers. And for R1, the type is the same, it's a scalar, and the range is included because 0 is included into 0 and 10. So yeah, that's essentially how it works. Again, it's a bit more sophisticated nowadays, but yeah. And jumping again to 2 days, I wanted to mention that like between the patch I showed you, like the very first patch and now, many heuristics were introduced to try to scale the pruning logic. So because we save a lot of states, some patch were introduced trying to create basically an LRU, least recently used map for the states so that we can prune all the states that we don't need. And an interesting talk was given by Jakub Kaczynski in 2019 at LSFMM BPF. And what he did is that he investigated on like real life progs, like Cilium progs, and noticed that every 4 instruction we had pruning points. So every 4 instruction, basically we were like saving new states. So patch were introduced later on. For example, when Alexei introduced bounded loops, to introduce more heuristics. Like this heuristic is pretty simple in a sense. It's just checking that before saving a new states, we came across at least 2 jumps and 8 instructions. So you can see we have like a lot of this heuristic in the kernel into the verifier these days. But Paul will now talk about like more like different ways to scale the state pruning logic.
Okay, so Mai explained the basics of state pruning, and we can see that it's very useful to scale the verifier to larger programs. However, in practice, when you get to larger programs and different paths, you're going to do different things on these different paths, and you may not always, have states included into one another. That becomes rarer, or more rare as the programs becomes bigger. So here I'm going to present 2 different optimizations to the basic of state pruning to try to scale it better, to make it more efficient. And they both rely on the same idea that we only need to compare what actually matters for verification. So when we compare 2 different states, if something doesn't matter for verification, we don't really need to compare it between the 2 different states for state pruning. And we also know that the less stuff we compare between these 2 states, the more efficient state pruning is going to be, because the more often we're going to be able to prune things. On the side, I've used an example I'm going to use for the following. It's similar to what Mai presented before. So we can see we've got 2 pruning points. We can also see 2 different paths because of the one condition. And we have a register R6 with a pointer to the stack. So at the beginning, it's pointing to the top of the stack and then to an offset in one branch and still to the top of the stack in the other branch. So let me just switch to the usual way of writing the BPF bytecode, or at least the usual way of seeing it. Same BPF program, same stuff. So I'm going to use this for the remaining. What we can also notice is that on instruction 7, and that's always going to remain on instruction 7, we've got a pruning point in this example. So I'll start with liveness. And in particular, I'll explain register liveness. So here, the idea, the rationale for this optimization is that some registers may be dead when we compare them. So a register is dead if the value it has at an instruction X is never used after instruction X. And I'm really talking about the value of the register. I'm going to give an example. So I have the same program as before. As I mentioned, we've got 2 different values for R6, so 2 different offsets into the stack. And R6 value is used at the last instruction for the memory access. So we know that it's written at instruction 4. we know that it's accessed at instructions 6 and 8 because of the plus equal for 6. So we know that R6 is live between instructions 4 and 8. However, because the value is overwritten at instruction 4, we know that it's dead just before instruction 4. So what that means is whatever the value of R6 was just before instruction 4, it's never actually used for anything after this point. So how do we compute this information? This is fairly easy to compute in the end. This is something that is done before the actual verification of the whole BPF program. It's done at the very beginning. And the idea is to go backward in the program. So we're going to propagate liveness going from the end of the BPF program and going backward. So we go from the read at the end. We see that it's actually reading R6. So it's using it. So it's live before the last instruction. Then it's live before the instruction 7 because it's not touching R6. Still live before instruction 6 because we're using it again. We're reading it again with the plus equal. Live before instruction 5. And then, as I said, before instruction 4, it's dead because we're overwriting the value. So this is a fairly simple example of how it propagates the liveness. Let's see an example with a verifier log. So if we're verifying the BPF program I just showed before, we're going to go through the first path. So same as May explained. We're going to see that R6 has a value of FP minus 8 on this first path. So at instruction 7, where we have the printing point, it has value R6. It has value FP minus 8. Then we'll verify the second path, and on the second path, R6 has a different value because we skipped the instruction where we changed the offset. So it has value FP0, which is the top of the stack. And because, as I've shown before, R6 at the printing point is live, we're going to compare the values, like the full thing between the two different states. So we're going to compare the offsets. We're going to see that it's different between the two different paths, and therefore we can't prune the second pass. So we're going to have the verification of both paths and of the full BPF program. Now I'm going to take this example and I'm going to change one small thing. I'm going to add a new instruction just before the end to overwrite the value of R6 just before the end. So when I do this, what we can see is that the liveness changed. So here I have two dots, meaning that in red, meaning that R6 is not live anymore in these two instructions. And that makes sense. Like if we go backward, we're going to compute this at instruction 8. We're going to see it's overwritten, so it's dead just before. It also makes sense because whatever we did before, like at instructions 4 and 6, doesn't matter for the memory access because that's not the value of R6 we're going to use. That's not the offset we're actually going to use at instruction 9. Now, the impact on the verification is quite clear. It's going to go through the first pass as before. We still have two different values on the two different paths, but when it reaches the printing point, it's going to see that it is not live anymore, it's dead, and therefore it doesn't need to compare the different offsets and the different, it doesn't need to compare this to the registers. So the state ends up being equivalent to the old one, and we can just prune the second path. And that's what we see with the save keyword here. So I've explained register liveness, but obviously we may want to do the same for stack slots. We may have dead and live stack slots, and we want to skip those that are dead. At a high level, this is fairly similar to the register liveness because we also want to compute which stack slots are read and written for each instruction, same as we did for registers. And we then want to propagate this information backward such that we can reach a stable state where we have all of the stack slots that are live across the whole BPF program. However, in practice, there's at least one reason, there's multiple, but at least one reason is making this more complicated. And that one reason is that to know which stack slots have been read and written, we need to know which stack slots we've accessed. And that depends on the offsets of the registers. To know the offsets of the registers, we need to go through the full range analysis that the verifier is doing. And that's only happening afterwards in the main verification from the verifier. So we need the range analysis to know this, so we need to accumulate the read and written stack slots as we go through the full verification. And that makes the whole implementation quite different from the register liveness. It makes it also maybe a bit more complicated And therefore, I'm not going to explain all of this here because it's taking a bit too much time with the time we have. And instead, we'll switch to the next optimization. But what you can remember here is it's still the same principle at high level, and we have the similar concept for the stack slots. So we've seen that the first one is trying to detect what is dead and what is live to avoid comparing what is dead. Now, the second one is called precise tracking, and it's going to do something specific to scalars. And in this case, what we want to do is only compare those that have values that matter. Because we know that the verifier doesn't always care about the values of scalars. To give an example, if you're computing some scalar, you're computing some value in a register, and you're just writing it into a map, it doesn't matter what the value of this scalar is. That doesn't make any change to whether the program is valid or invalid, because it's just written into a map. However, if you're taking this value and you're, for instance, returning it from your BPF program, and if you have, like, for instance, an LSM BPF program where, if I remember correctly, you're checking the range of the return value, you only have certain return value that are expected, that are allowed. In this case, you're using the value of this scalar of R0. So in that case, you do care about its actual value. And that's the example I have on the side. So on the side, I have similar example as before. We still have the printing point at 7. We still have 2 different paths. But on the 2 different paths, we're going to have register R0 with 2 different values. So on one path, it's equal to 0 because of the condition. And on the other path, it's equal to 1 because we write 1 into it. And in this case, if exit is checking the range of the return value, then we care about R0. So how do we compute this in the verifier? It's a little bit similar to what we did before, meaning that when scalar values are used for verification, we're going to mark as needing precision the register for the scalar value. And then we're going to backtrack this information through this same register in previous states, but also to anything that contributed to the value of this register. So if you added something into the register, then the precise value the register has depends on that thing you added. So let me dive a bit here. What does it mean first for a scalar value to be used for verification? So I've given one example before with R0. If we're exiting and checking the return value, we want to mark R0 as requiring precision. Another example that's easy to understand is if we're calling a helper and that helper has a size argument, the verifier is going to check the size argument. It's going to check that it makes sense with whatever other information it has. And in that case, we also want to mark the register holding this size argument. And we have like lots of other different cases for this. We've counted 11 different cases of when we need to mark a scalar as needing precision. So now let's go into the backtracking side of things. Here, the implementation is a bit different from what we've seen before. It's maybe somewhat similar at a high level to the stack slot backtracking, but it's different in the implementation. So the idea here is to maintain a bit array of what needs precision. So we're going to have in the bit array bits set for each register and stack slot that needs precision. And we're going to use this bit array and maintain it as we go backward through the program. So we're going to try to propagate the precision information, like what needs precision, as we go backward. We do that using the jump history. I'm not going to explain what the jump history is into too much details, but what you can remember is it's a way basically to go backward and remember where we came from in terms of jumps, basically, in the BPF program. And then we're going to use propagation rules for each instruction type to know how to propagate the precise marks. So I've given 2 examples here. The first one is destination plus equals source. So that's a type of instruction. If the destination is marked precise, we know that the source contributed to its value. So we also need to mark the source as needing precision. Another example is if we've got destination equals some immediate value, then we've overwritten the value of destination. So if it was marked precise before, we can clear the mark because nothing before that point is going to contribute to the value after this point. So let's see an example again of how this works for the verifier. we're going to go through the example I've shown before, so the small BPF program with R0 and 2 different values. We go through this example, and when we reach the exit instruction, we're going to mark R0 as needing precision, and we're going to kickstart the backtracking. So we see this in red with mark precise colon. Then in the backtracking, we'll reach instruction 8. At this point, we know that the only register that needs precision is R0. And we also know that the stack slots don't need any precision. So we've got stacks equal nothing. And then we can notice that R0 has a new value assigned, so we can clear the mark on R0 as I explained just before. And because of that, we don't have anything more to propagate. We don't have any other precise mark, so we can stop at this point with the backtracking. Then we use this information on the second path. We see that we've got the jump from 5 to 7, so we jump across the instruction 6, and we verify the second pass. Then we reach 7, where we have the pruning point. And at this point, because R0 was marked as not needing precision in our example before, remember that we stopped just before, we stopped at instruction 8, then we don't need to compare the values of R0 on the 2 different paths. So it doesn't matter that it has like value 0 on one path and 1 on the other one. That doesn't really change anything for verification. So we can just say that, yeah, it's safe to go on and we can prune the second path. So to conclude, state pruning is a verifier optimization that allows us to walk less path during the verification. And today, it's probably the main way to scale the verifier, at least it has been for quite a while. And that also means that it evolved a lot over time. So we've seen some examples here, and we've only presented for the register liveness, register liveness, tax liveness, and precise tracking. I've presented the latest implementations, but before then we had like other implementations, so it changed quite a bit. While we were going through all of this, when we started, we didn't know much about all of this. So at least I didn't know about the liveness, for instance, for stack slots and even for registers. So we've started writing a lot of stuff around this. So we wrote workthroughs, examples, documents, and we're probably going to publish some sort of blog post or something to try to have this information out. I've listed examples before of like lots of different cases. I only cited a couple, but we have more to share. We also have some ideas for like logging and documentation that could change here. So Mai presented one that was useful for us to verify a bit like what is happening at runtime. So that may be something useful to try to upstream. And there's also like a lot of questions around the pruning points because they changed a bit over time. They haven't changed in quite a while. And also the BPF programs are also changing nowadays. The usage is a bit different. So it's not always clear if what made sense at the time is still making sense today. So there's probably an opportunity to try to investigate a bit more if all of the pruning points we have are still useful or if we need others. And I guess that's always going to be sort of something to verify as we go. And with this, I'll conclude the talk, and I'll be happy to take any questions.
So when you cannot prune, do you consider sometimes to take a union of states instead? You will lose precision this way, of course, but it's probably better than verify saying that your program is too complex.
Yeah, that's a good question. So, so what you're mentioning is basically something called what's the word? Widening. Thanks. So widening in the formal method part. So, for instance, in abstract interpretation, that's called widening. It's something that the Windows verifier is doing actually. So the Prevail one is doing this. It's doing widening in this case. It's not always helping because it can be a bit tricky to know how much to widen, basically. And in some cases, you can lose precision because you're doing this. So I guess there's always, like, in both cases, you're going to lose precision. And depending on how you're verifying the program, it can be more useful to do one or the other. So yeah, but I mean, there may be cases where it's useful. And I think there's something resembling a bit widening for the loops nowadays in the verifier. So maybe Edward is going to say something about this.
Sorry, I can address the thing about widening.
So we would do very limited widening. We do it for iterator-based loops. If on a second iteration of a loop we see the scalar which was not marked as precise, we widen it to unknown. And it is like actually crucial for iterator-based loop convergence. But it is like very imprecise. There are like ways to make it better. Yeah.
All right, we are on time. This is perfect.
Okay. So, yeah, sorry. Yeah. Yeah, so the name of the presentation is a little bit generic, and it was supposed to be like a hodgepodge where I overview like what happened last year for loops verification. But yeah, I'll first start from the most interesting topic, which is right now in progress. The topic is scalar evolution. And scalar evolution is basically a way to infer loop iteration bounds, or basically like algebraic expressions for values which change inside the loop. So like in this example, the goal of the scalar evolution analysis is to infer like that variable I changes as an equation, like some initial value and +2 like every k times. And in order to infer the loop iteration bounds, you have to solve an equation like inequality with respect to k to infer like how much times the loop can iterate. So this is the analysis which is performed by both LLVM and GCC, and we kind of borrowing from the same papers they do. And the analysis completes of 3 steps. On the first step, we do a single pass over the loop body and collect algebraic expressions for values that change inside the loop. Then, using these expressions accumulated on the loop header, we infer recursive relations, like basically these recursive formulas, describing the law by which values change inside the loop. And then, using the information calculated for the loop header, we propagate it to the expressions inside the loop. And looking at specific example, here is a simple loop where register 0 is always updated by 1 inside the loop body, and register 1 is updated conditionally. And so for the first step, the collection of the algebraic expressions on one loop iteration. Like the interesting part here, like on the right, I show like state of the analysis before instruction is processed. And interesting instructions is from 4 to 5, where you can see that R0 survived it like as is before, like from the loop header, R0 didn't change. Or like, well, yeah, while analyzing the loop from instruction 1 to instruction 4, value of R0 had not changed. But the effect of the instruction 4 is basically that R0 becomes R0 plus 1 compared to its state at the beginning of the loop. While for register R1,
At the same instruction, there are two possible values for it. Either it's an initial value of R1 or an updated value, R1 plus 1. And in this case, we bail out in order for all analysis to converge and just replace R1 with unknown. So basically, we arrive to the loop header with algebraic expression stating that R0 after one loop iteration is R0 plus 1. From this expression, we derive a recursive relation like that R0 is a simple linear equation. And then we can use this information to infer, for example, what would be the recursive relation for R0 at some other instruction inside the loop. For example, at instruction 5, after R0 plus 1 is processed, we already know that the algebraic expression there is R0 plus 1. So we just substitute R0 with the recursive relation we inferred, and we get a new recursive relation for it at the specific point inside the loop. Now, we can only partially borrow from the papers describing this analysis and from the LLVM or GCC implementations, because they work like on intermediate representation, like on some C-like language, where you still have a notion of variables or SSA values. Unfortunately for us, we work on the assembly level, and tracking of like register ranges require in presence of stack spills and fills requires tracking which stacks are actually spills and fills, and vice versa. So this simple program illustrates the problem. So you see here a simple loop where register 0 is a counter, and it is spilled on stack at the beginning of the loop and filled from stack at the end of the loop. And there is also a stack access in the middle of the loop. And in order for scalar evolution to correctly infer the algebraic expression for R0, it needs to make sure that the stack access inside the loop doesn't actually override the spilled value. But we can guarantee this only if we know, for example, here, what would be the range of the register R1. So yeah, this is a cyclic problem. In the literature, it looks like the most common approach to attacking this is named value set analysis. It is a classic abstract interpretation analysis, and it uses like interval abstract domain accompanied also with trained information for a variable. So actually, like each value in this analysis is represented as a tuple. First element describes which region the element belongs in. Is it a stack memory? Is it malloc memory or something like this? Minimal value, maximal value, and step with which the value changes. And yeah, as a classical abstract interpretation analysis, it corresponds of the widening and narrowing phases. And like this is both similar to what we do in BPF verifier and very different. We don't do states join, while a classic abstract interpretation does state joins. So on the one hand, it probably would be interesting to someday convert verifier to this architecture. But for now, we want to avoid like two big changes. So one workaround, which is currently a backup solution, is to sidestep this problem completely and introduce a new like register R11 and use it to track stack spills and fills. So basically allow two instructions using this register and modify, and lower this R11 to R10 after the verification is done, and modify LLVM BPF backend to emit R11 instead of R10 for stack spills. And an example of lowering would be like during program verification, verifier identifies the depth of stack used by subprogram. So knowing this value, we can simply shift all offsets for R11 by this value, and thus allocate us some space for these temporary variables. Yeah, so this is simple to implement, and we have prototypes ready for this, but the obvious drawback is backward compatibility. So another workaround, which is currently work in progress, is to do scalar evolution analysis before the main verification pass. And whenever the expressions of form rtan -8, -16 are used for stores and loads, assume that those are actual honest stack spills and fills for values which will not be aliased. But also record this information alongside the expression. Later on the main verification path, when use this inferred information about like formulas by which different register changes, record in the verifier state under which assumptions this path would be like correct. The information about value ranges would be correct. And if at some step of the verification process we see that this assumption isn't valid, just abandon the corresponding verification path, saying that we cannot proceed. Yeah, basically back up to the bounded loop verification scheme, which is currently implemented. So as for the example, for the initial example, scalar evolution will compute that for this program at loop header at instruction A, R0 changes like by increment of 2, under assumption that stack slot R10 -8 is not aliased and is only accessed via direct instructions. And at step B, same scalar evolution path will infer that the value of register 1 changes by 8. So given some initial conditions like R0 equals 0 and R1 -56, verifier will enter instruction A, having a state like it will infer that loop iteration bounds is between 0 and 5, and it will proceed with the state R0 is 2 times loop iteration number, R1 is -56 plus 8 times iteration number, bounds for the iterations number, and current assumptions, which are R10 -8, accessed only directly. So at point B, it will so happen at point B, it will so happen that R1 is within bounds that preserve the assumptions, and on the second, the basic idea of this example is that under these initial conditions, at point B, the condition holds, and verifier can proceed with verification of the shortened verification of the loop. Under some other initial conditions, at point B, verifier will identify that overwrite of stack slot -8 might happen and abandon this verification path. And as for nested loops, handling, like more sophisticated schemes are possible, but what we are aiming currently is nested loops are verified before outer loops, and any values modified inside the nested loop are used by the outer loop as an unknown value. And for the outer loop, the nested loop is represented as a single control flow graph node. So basically, it should work for simple loops when you have like independent loop variables and don't change like counters inside the nested loop body. So the current status for this is loop structure reconstruction. This works. Loop structure reconstruction is like identifying the nesting, identifying the loops and identifying the nesting hierarchy for the loops, and also identifying what conditions dominate back edges to the loop and exit from the loop. Collection of the algebraic expression is done, nested loops are handled, and recursive expressions construction is in progress. So that's that. So before I proceed with other topics, are there any questions about scalar evolution? No questions.
John is asking the question. Can you see it?
Okay.
Sure.
So go-to into the loop is not really a problem. The problem might arise with irreducible loops. And the reducible loop is a loop with multiple headers, like when you have several entries to the same loop. And statistics I run on self-tests and on some internal programs, we actually have 0 instances of irreducible loops. And because like loop structure reconstruction is not pattern-based, we just implemented a few algorithms on the control flow graph. It is generic, so whether the loop was coded, it doesn't matter how the loop was coded, whether it was go to, while, for, and so on. As long as it is not an irreducible loop, it should be fine.
Thanks.
Okay. So 2 other topics. Another thing happened like this year is we identified one more iterative correctness bug. And this bug was related to read and precision marks propagation. And it triggered like a significant redesign to several subsystems. So the culprit of the bug, like the example program which demonstrates the bug, is here register R6 can be either -32 or -31, and it is also used for stack access 8-byte width. So unaligned stack access is possible, but before the fix, the verifier didn't notice it. And this happened because verifier cached at instruction 6 a state, which was considered fully explored, with R6 equals -32, and R6 didn't have a precision mark because this state was cached before the branch from 9 to 10, where R6 is actually used in the precise context, was explored. Consequently, when exploring the outer branch from 4 to 5, when R6 was assigned -31, this state was considered equal to R6 equals -32 because -32 lacked the precision bit. And yeah, so I'll probably skip a bit about the root cause. The main problem is that when we verify iterator-based loops, we do a shortcut. We allow verification to stop early before reaching an exit condition from the program. We actually stop the verification at the iterator next call. And this introduces a loop. And when we terminate some verification path, we need to propagate written precision marks from the state, from the cached state. But written precision marks are incomplete at this cached state yet, because we are within the loop. So the correct thing to do is to actually accumulate all these states and do the written and precision marks propagation like several times whenever the marks change in any states that belongs to the loop. And unfortunately, this didn't happen. We didn't realize that this is a problem. So to solve this problem, we introduced a notion of strongly connected components into the verifier. Like before the main verification pass, we compute strongly connected components on the program control flow graph. And then on each verification pass, whenever some states enters strongly connected component, this state becomes an entry state. And as long as the state has some children, some unexplored children, the whole strongly connected component is considered not fully explored, and any red and precision marks within this component are ignored. And this strongly connected component with it, it also becomes a unit which accumulates this state graph back edges. Once, so before the loop and the strongly connected component, like loop entry state, is fully verified, we treat the whole component as not fully verified. And as soon as this state becomes fully verified, we assume that the written precision marks for any states within this strongly connected component are correct. Okay, and this triggered like another change. This accumulation of the state packages on the strongly connected components, it requires accumulation of the complete state graph within the strongly connected component. So as many states as verifier visited, whether we want to cache them or we don't, because there is some logic to evict caches, states from the cache, they have to remain in memory in order to do the written precision marks propagation. So that's one thing. Another thing is that thinking about this states loop is complicated. Like, for example, when I identified the previous bug, I spent, I think, like 2 days before I was able to formulate the actual self-test demonstrating the bug. And the second problem with this propagation is that if at some point we will have an oracle which will be able to predict the loop bounds and magically tell us, like, before the main verification pass bounds for different values, we will not be able to use this written precision marks propagation analysis in combination with it. We will need something else. So an alternative is to propagate the written precision marks on the program control flow graph instead of the verifier states graph. And this is partially done. We currently propagate read marks on the control flow graph. We don't propagate precision marks. We have to do that. And as a nice bonus alongside it would be that we will reuse most of the code between read marks tracking and precision marks tracking. Okay, and so the basic idea is to basically do the same thing which is done for register slots, just a textbook live registers analysis. But because at the moment we don't have any kind of prior range analysis. Our range analysis is the main verification pass. So we split the live stack analysis in two phases. The first phase is write marks accumulation, and the second pass is read and write marks propagation. So as each instruction is verified, we note which stack slots were read by it or which stack slots were written by it, and whether it happened like always. And whenever we need to do some state pruning, for example, whenever we need these read marks, we do another round of marks propagation, basically, and data flow analysis on the marks we accumulated to this point. And handling subprograms was actually a little bit tricky because subprogram, depending on the call site, it can modify different stack slots on the in the parent frame. And it turned out that tracking this difference is important for verifier performance. If we melt like to some kind of generic outer frame number 0 modification by the program, we lose too much information. And some of the SCADEX programs, for example, stop to verify. And to accommodate this, we basically keep like separate instances of each subprogram for each possible call chain. And within this instance, we accumulate the read and write bits. And then use this information at the subprogram call site to understand the effect of the subprogram call as a whole. Yeah, so that's all I had. So I guess it's a break time.
No questions? Everybody understood? There is a quiz at the end.
So do you think it's possible for us to offload some of the past analysis to user space? That is, say we have some academic like annotation approach where in the BPF instruction set we could annotate maybe the past header or the exit the prune point. I'm not sure what I'm saying, but anyway, could you annotate something that for the user space to tell the verifier that, hey, the looping condition is like this, and the verifier tries to check it. And would that work, and would that like offload some of the complexity?
Well, the current inclination is to first make sure, make sure that we cannot handle this inside the kernel, like using reasonable implementations. So you're probably referring to like a submission a couple weeks ago to the mailing list where some of the work was offloaded to the CVC5 solver, I think. Yeah, yeah. So what we are discussing currently for that patch set is like we want to identify all the cases where verifier falls short and to see whether we can implement like reasonably simple tricks inside the verifier to make it pass. So we are not done yet. And this resorting to user space, I don't even know if Alexei will accept it at all. But yeah, currently we are trying to avoid it.
I wasn't aware of that, but thank you so much.
So now we'll have a 30-minute break, right? So yeah, see you all back at noon.
No, I
So
think
when
it's
you're
yeah, I think you mentioned the website, but oh, I also
stuff is higher.
yeah.
Can you go from there?
I'm trying.
Like super slow. But first, can we delete the old ones first?
Right. Yeah. Yeah.
Hello. So it's noon again, and we're continuing with the next presentation.
Hello, everyone. My name is Yiming. So today I will present my project, ePass. I started this project during my undergrad with Ryan, and I'm a PhD student at UT Austin now. So ePass is a framework for enhancing the flexibility and runtime safety of eBPF programs. So let me first do a brief introduction to the eBPF. So it's a kernel technology to extend the Linux kernel, and it's widely used. And it has many benefits, like you can add kernel features without modifying the kernel, and it's safe and efficient due to the verifier, and has wide use cases like for network, observability, security, and there are more use cases. So this is the current eBPF architecture. Users will write eBPF programs, usually in the limited C language, and they use LLVM compiler to compile it to the bytecode, and they pass the code to the kernel through a BPF system call, and the verifier will judge if the program is safe. And if it is proved, it will be passed to the GT compiler, and you can attach the program to some hook points in the kernel. And the program will interact with the user space through the eBPF maps and through the helper functions. Okay, so here's a well-known problem, which is called the verifier hell. So currently, the verifier uses like the symbolic execution approach. It checks the safety of the programs against many rules. And we found that this approach caused some inflexibility and vulnerability. So first, we found there's a limitation about the flexible data structure. So nowadays, like eBPF has many more complex use cases, like CPU schedulers, cache extensions, and they usually require richer data structures, like linked lists and trees. But the dynamic allocation and like pointer chasing are restricted in the eBPF because the verifier restricts that. And the recent systems like kflex and extension, they work around this by adding some custom helper functions and kfuncs to support their custom complex structures. But this approach requires modifying the kernel. And the second limitation is about false rejections. So many researchers and developers have reported that the verifier is too strict and rejects many programs that are actually safe. And those are some examples from the real-world projects. And a third limitation is about the dynamic security issues. So as you can see on the right-hand side picture, like there are like 45% of the CVEs in the eBPF subsystem due to the verifier itself, but there are also over 50% of them due to other components like the eBPF helper function, kfuncs, and JIT. So those may also cause vulnerabilities. Moreover, like the verifier itself can have some bugs. So you can see the verifier size grows very fast. So it's already over 25,000 lines of code. And there are many bugs in its implementation. And they are like for various reasons, like the null pointer dereference, out-of-bound access, and many different reasons. So there are some existing approaches to solve these limitations. One approach is to improve the static analysis. So there are some existing work. And some of them are using like formal verification methods, and they are very effective. And then another approach is to add runtime mechanisms, and there are already some work adding the runtime mechanisms, but they only focus on a specific use case, like they only support dynamic loop or sandboxing the memory access. So we think that we need a more general and flexible approach to improve both flexibility and safety. So before we show how our ePass could solve these limitations, let me first give an introduction to the design of the ePass. So it's implemented as an in-kernel framework that operates before JIT. And it's actually a compiler framework because we believe that like the program transformation could solve those problems. So we have several design goals. We want it to be flexible. So we allow developers to conveniently analyze and manipulate the eBPF bytecode. For example, you may want to implement a runtime check. And we also want to make it safe. So you can enhance the safety while minimizing the attack surface. And we also designed it to be a verifier cooperative. So our ePass could use the verifier's analysis results, and the verifier may also call ePass. And it should also be high performance. So we want to minimize the both static and runtime overhead. So since our ePass is implemented in kernel, so there might be a concern about whether it increased huge TCP. So we think this is not true because we did not modify the original eBPF components like the verifier or the JIT. So like all the original eBPF safety rules are not changed. We only collect information from the verifier. And all the instrumented eBPF programs, they still need to go through the verifier to ensure the original eBPF safety properties. So here is an overview of our core. It's a compiler framework that provides some functionalities to manipulate the eBPF bytecode. So you can see it first lifts from the bytecode. We have a lifter that lifts from the bytecode to our ePass IR. And then we have many passes that will transfer this IR. And finally, you have a code generator that compiles the IR back to the eBPF bytecode. So here's a sample workflow. This is a loop counter pass, so it's adding a counter for the loop. So in the first picture, this is the original eBPF bytecode. And the second picture, we lifted to our ePass IR. And the third step, we are running the counter pass. We transform it by adding several instructions, like adding the counter. And finally, we compile it back through our code generator. And this is the final eBPF bytecode. And our ePass core provides some comprehensive set of functions that users can use when writing their passes. So as you can see, we have instruction manipulation APIs, basic block manipulation, and verifier integration APIs. So the verifier integration APIs allow you to get the verifier analysis result. You may get like for example, the range of register. And we also have some convenient function you may use. And for our IR, first, it's inspired by the LVN IR. So we also provide similar features like we are in SSA form, we have virtual registers, and we have a control flow graph and file instruction. So we benefit those things from the LVN. But our IR is designed to be more lightweight, and it will be specifically tailored to the eBPF bytecode. So first, we have our own instruction set, which has 3 categories. First, we have instructions that directly corresponds to the eBPF instructions. And second, we have general instructions used during the transformations. For example, you have allocate, store, and get element pointer. So those are the instructions that are convenient for the program transformation in your pass. And we also have some eBPF specific instructions, not in the eBPF ISA. For example, we have a throw instruction that terminates the program safely, and we have a eCall instruction. This is a virtual instruction to support complex operations in eBPF, and we have a use case for that, and I will explain that later. And we have untyped virtual registers. So currently, we do not have a full-feature type system, but we record the value size for correct compilation. And we also have an IR checker to make sure the syntax is correct. And we keep the original eBPF load and store memory instructions to preserve the stack layout. And another important feature is that our IR is annotated. So during the lifting, we all annotated the IR using the bytecode information. So this is an example. So you can see that all the virtual registers, we record its original position in the bytecode. And for the values, we also record its original position. So that will be useful when you want to use the verifier analysis result. And here's a table showing some of our IR instructions. And now let me talk about our pass design. So we want to make our pass very flexible because users may have many different purposes to use our passes, and we also want it to be highly configurable. So each pass may have its own parameters, and we provide in-verifier and post-verifier passes. And we have an IR checker to check it will run before and after running each pass to ensure the syntax is correct. So for the IV and PV passes, we designed this because we noticed that different passes with different purposes may require different ways and stages to run. So for example, if a pass is used to handle a verifier error, then it probably need to run multiple times, and it's an IV pass. And for example, there are optimization and some runtime check passes. They only need to run once at last. So those are like PV pass. And this is our supervisor. So it will build an execution strategy to run all the passes. And we have this verifier information. So the PV passes, they run after the verifier. So how can they access the verifier state? So we provide a verifier information map. So it's a mapping that maps the instruction indices to the corresponding analysis results. And this VI map will be constructed during the verifier's verification. And you can use this find IR instruction by RAWPOS to get the verifier information for all virtual registers in the IR. And you could also add any verified data to this map on your demand. Okay. And now let me show some our use cases. So we implemented several passes that covers many different purposes, including flexibility and security enhancement and optimization. So here we selected some to show. First is our heap pass. So this pass is used to introduce more advanced data structures. To do that, we need a mechanism to allocate memory dynamically. So we emulate the heap memory by using a eBPF map as the backing store. But there's still a problem. The pointer tracing is not possible because the verifier restricts that. But since our ePass is a compiler framework, it could transform the store and the load instructions to use this fake heap. And we provide eCall instruction, this malloc and free, and they will do the real allocation and deallocation. And by default, we support a fixed size block-based allocator. So this is a very simple allocator that would be possible to implement in the eBPF bytecode. And it has a good performance in simple cases. And we also allow users to define their own allocators in the eBPF program. And they could also only use our heap pass to transform the memory access to resolve the pointer tracing issue. So this pass is quite flexible. So here's a sample walkthrough. So here is the C program user will write. So you can include our helper header. So in this header, it defines the maps and the malloc and the free functions. And internally, it will construct an instruction that not exists in the original eBPF ISA, but our ePass could recognize it. And this function, this program will be first compiled to the bytecode, and then will be passed to our ePass core. And our IR recognize these eCall instructions, and it will convert those eCall instructions to the the real instructions that construct the heap. Yeah, so that's how it works. The second use case is this loop counter pass. So many developers have encountered like the verifier's instruction limit rejection. So the reason for that is they use some loops, and the verifier is unbounded. And another reason for that is the verifier's current static limit calculation is not very accurate because it only counts how many instructions it processed. But a program may have like at runtime it has a very different path. So developers usually need to manually use this BPF4 and BPF repeat to express loops. So our this path could add this runtime instruction counter to the loops, causing the verifier rejection. And we will derive the best bound for each loop from the verifier's static analysis result. So actually, there are some technical details here, but we hide it here. So basically, we will derive the best bound and insert that counter for your loop, and then your program could pass the verifier. So you don't need to use this BPF4 or BPF repeat. And our third use case is a helper validation pass. As I said before, the verifier has no way to ensure that like a helper functions are correct. So those are like outside the verifier's domain. So this pass will add some runtime checks for the return value of the helper functions to make sure that they fall within the verifier's expected range. And we think that a further use case would be to check like more functions like the k-funcs. And our third use case is for this instruction counter pass. So there's a problem with the current tail call mechanism. So tail call is not tracked by the verifier for the instruction limit checking. So attacker could construct a very long chain of tail calls to bypass the original limit to do like, for example, DOS attacks. And also like implementation bug may also lead to like infinite tail call. So this pass, we add an instruction counter for the BPF programs. We insert a dynamic instruction counter to track all the executed instructions. And the counter is stored in a per CPU map, and it will pass across tail calls. And each program will read and accumulates that counter at the entry. And this approach, since it's like the runtime counter, so it will be more accurate. And the execution, it will stop the program if the counter exceeds 1 million instructions. Okay. And another use case is this MSAN pass. So it's a memory sanitizer. So we found that the verifier does not track the uninitialized stack memory in the default mode. And in the non-root mode, the verifier tracks the uninitialized stack memory in an inaccurate way. So it only tracks the deepest used offset and assumes all bytes above it are initialized. So we designed this pass to do this memory sanitizing more accurately. So here's an example. We construct an array and initialize the last element, and we access this array using a variable x. So we need to assume that this x is is a valid index. So and we read this value from the array. So this should be an uninitialized memory, but the verifier does not reject it. So this is the problem we found. So our pass will construct a shadow memory in a map with the same size of the original stack. And we will add instructions after all the store and before the load instructions to set and query the shadow byte. Yeah. And another use case is this masking pass. So we found that there's a gap between the LVN compiler and the verifier. So here's a short example. We have two code. So basically, you can see we are using this ID to access this array. And you can see that we already did this index boundary check, but those programs are rejected. So the reason is that the LVN knows this helper function returns a positive number. So it optimizes out this line 5 and line 6, but the verifier does not know that, and it requires that boundary check. So it is rejected. And to solve this, developers need to manually insert the AND instruction to mask the index. So this pass will automatically add these masking instructions if the verifier reports like there's a out-of-boundary access to a map. Yeah, so this is the basic idea. And finally, there's a runtime validation pass. So we want to capture some verifier internal bugs. So here's a example. This is a CVE that will cause the kernel pointer address leak, and attackers can get the root privilege. So the root cause is that the verifier thinks the argument to this helper function is 8, but at runtime it's actually 9. So it's due to like the verifier's internal derivation errors. So what we can do is just adding this range check before calling these helper functions. So this is based on the spec. So we are adding those instructions here. And this technique is called the dynamic parameter auditing. This is from another project, but we generalize this technique to a more general path that can be applied to like more helper functions. And we will perform those running checks for like the argument of this helper function call based on the verifier's expected value ranges. So it can mitigate many similar exploit caused by like any verifier derivation bugs before causing any side effects. And for implementation, we implement our ePass in like 12,000 lines of C code, and like our implementation guideline is to make it flexible, simple, and easy to test. So one feature I want to mention is that our the core compiler could be compiled and used in user space, but you may not use the verifier information. But it's very useful for debugging and test. So here's our command line interface. So you can use this in user space. You can run for example, run some passes, passing this pass option. Yeah. And we will also provide a libBPF and a BPF tool with our ePass support. So you just need to enable ePass through the environment variables. And like any application depend on the libBPF can use ePass. And we also have like user-friendly error message. So if you have some bugs in your pass, then we will have a very user-friendly error message to report to you. And finally, I will give a brief introduction to the experiments we did. So first is for the flexible data structure. We implement a linked list and binary search tree using our heap pass, and we also implement the same data structure in a kernel module. And we found that and we tested the latency. So the result is that our eBPF code is actually faster than the kernel module. We think that the reason is we use a simpler allocator, because in the kernel module you will use the kmalloc. But for our allocator, it's very simple. So since the data structure has a fixed size, so it's faster. And it's, especially for the free operation, it's much faster. And for the false rejections, we collect many programs with different root cause and different categories, and we resolve many of them. And for the security, we also collect many CVEs, and 4 of them have the public proof of concept code, but others don't. We think that they share the same concept, so we think that ePass could help those CVEs. And we run some benchmark to test the runtime overhead. So we first test these XDB tools with our counter and MSM pass. So you can see the overhead is not that much. And for the numbers, we have a benchmark on Focal. So you can see the average runtime overhead is like about 2%. To conclude, our main contribution is we provide a new IR for eBPF and a path-based compiler framework. And we allow developers to extend the expressiveness of the original eBPF language. And we allow developers to add runtime checks, optimizations easily. And we enhance the flexibility and safety of the eBPF programs. And that's all. Thanks for the attention. So here is the GitHub repo. We are currently developing it, and we welcome any feedback and suggestions. Thank you.
As I understand it, the JIT compiler uses information from the verifier when it's emitting code. Yeah. How can you have passes that operate after the verifier runs that generate new BPF code if that information from the verifier therefore isn't available to the JIT compiler?
So after we instrument the code using our ePass, all the code will be also passed to the verifier to do the final check. So the verifier will have that.
So you run the verifier, run the in-verifier passes, continue running the verifier, then run the post-verifier passes, and then verify it again, and then do JIT compilation. Yes. Okay, yes. Thank you.
So because we need to make sure that all the instrument code have the same security, like the properties. So we make sure that the programs will pass the verifier. Yeah. Thank you.
There's a question in the chat. Is it Valgrind inspired too? It's very reminiscent of it. If like if this work was inspired from Valgrind, the memory checker.
Memory check? You mean the MSAN? Or which one?
I don't know. Maybe that person can speak up. Who wrote the comment in the chat?
Oh, check. I see. So that's for the MSAN pass. I see. Yeah. So we implement our MSAN pass to show that our you could write a pass that to track the uninitialized stack. So that's like an example to show like we could do some security use cases. Yeah, I think the Valgrind is also good. Yeah. Yeah. Thanks for the comment.
The link that's showing is all the code is available there.
I'm sorry.
All the code is available there. So all of these examples that you showed, including all of the paths and lowering and lifting into this IR, and it has like documentation on the what IR, like what instructions you're defining in your own IR.
Yeah.
Okay. Cool. Thank you. This is impressive work.
Thank you.
So now I'm going to talk about a new test oracle to help fuzz the BPF verifier. So this talk is going to follow the usual outline. I'm first going to talk about the issue here that I'm trying to solve, so testing for false negatives in the verifier. Then I'm going to cover some background on this, so some related work. And finally, I'll go into the idea, its implementation, an example of it, and some open discussion. So what's the issue here? So the issue is that today's fuzzers that are covering the BPF verifier are actually quite good at covering some of the issues that we can find. So for instance, memory errors, deadlocks, some kernel warnings, usually minor kernel warnings, are regularly found by Syscaller and Sysbot. However, these tools, and not only Syscaller, struggle a lot more to find false negatives in the verifier. So stuff that the verifier is accepting, BPF programs that the verifier is accepting, but shouldn't actually accept. And the struggle to find this because these bugs are typically silent. When the verifier accepts something it shouldn't, it's obviously not going to say that it did something it shouldn't do, otherwise you wouldn't have a bug. So to solve this, we need some way, some sort of test oracle to be able to say we've had this sort of soundness bug, we've had this sort of false negative. Fortunately, there was an academic paper in one of the top system conference last year, so at OSDI, and they tried to address this exact issue in BPF. So I'm going to quickly present the idea here. I'm using a small example on the side. So the small example is starting with spilling an immediate value into the stack, so -1, a negative value. Immediately after that, we just fill it back the same value into R1. Then we do some stuff with R2, but basically we're just making the value of R2 depend on R1. So we're checking if R1 is negative or positive, and based on that, we'll have different values for R2. And then we exit. So I'm going to take this and follow what they do to find false negatives. So first, the thing to know is that the way they want to find false negatives is just trying to compare the concrete values from the runtime with what the verifier is expecting. That's sort of the idea here. The way they do that is a bit more complex. So they start with this accepted program, and they're going to first trace it to retrieve the concrete values for each of the different variables. So registers, also potentially stack slots, but here I'm only showing registers. So R1 and R2, we're going to trace it to get the concrete values. Then once it did that, it's going to take these concrete values, take these registers and fold them into a new register. So here I'm using R9. We're going to fold the different, so basically do some sort of, I guess, hash function in a way over these registers into one single register. And why do we do that? We do that so that we can check the value of this new register. And we're going to compare it to, in this case, -1. So basically, R9 computed over the concrete values we traced at the beginning. If it's the same value, then it's working as expected. And in that case, we're not going to take the jump. So basically, if it's working as expected, it's going to go into this verifier thing, which is throwing a BPF verifier error. So if we do get an error after modifying the BPF program, we know that there is a false negative. If we don't get an error, there is an issue. If we do get an error, we know that it is working as expected. And if we don't get an error, we know that there is an issue, right? It's just reverted. Okay. This sounds a bit complex, right? I think it's more complicated than it needs to be, or it should be. And I'm guessing the reason for this is that they try to limit the amount of changes that they make into the kernel. That's often like a parameter to evaluate academic papers. So it's usually, if you want to pass into conferences, it's best if you can limit a bit how many changes you made. But in this case, I'm not sure it was the best idea. Maybe it would have been better to make more changes. It's also limiting the precision of the results because you've folded different values into one single register. So if you've got different issues and maybe the hash function doesn't really expose these issues because it hides them, then you're going to lose some information here. You're going to miss something. And for the same reason, it doesn't directly point to the issue, to which register was having like an incorrect value, because you folded all of this into one single R9. So it doesn't point directly to where the issue is. You may need a little bit more debugging to get to this. So if you've attended the BPF track last year, maybe you remember some of this because I already presented it last year. And when I did, oh yeah, okay. So one more thing I didn't mention before is just that this approach is not open source. So they use a whole new further using this approach. So they developed a whole new further on the side. It's not open source, and also all of the bugs they found, I think they fixed 9 or 10 upstream, but they mentioned 15 in the paper. So I don't know. I tried to reach out, but like, yeah, it didn't go anywhere. So I presented all of this last year, and when I did, after the talk, I think Dmitry had an idea that maybe we could simplify this a lot. So try to get to the same results, but with a simpler approach. And the approach is basically taking the same, I guess, initial inspiration as the academic work. We want to compare the concrete values to what the verifier has. So here the idea is to save the states during the verification somewhere, and then at runtime, check the concrete values for the registers or the stack slots with the state we've saved. And if we check this directly with the verifier results, we won't have any folded value. We get a better precision. We get something a bit immediate, like we'll have bug reports pointing exactly to what was the issue in the verifier states. So I implemented the first POC of this. It's on the mailing list. Please take it as an RFC. It's like very rough. There's still like maps leaking in some case. I think it's missing the RFC tag, but you get the idea. The scope for this first implementation is very limited. It's just to show the ID. So I've limited it to just registers. It's only checking registers. On registers, it's only going to check the ranges for scalars and the tnums. And then at runtime, it's only checking this in the interpreter. So basically, you need to enable the interpreter just because it was a bit easier to implement for a first version. Then it saves and tests this information at the printing points. Again, that was a bit easier for first implementation. So at every printing point, it's going to save this small information I'm gathering on the verifier states, and then it's going to check it again at runtime on the printing points. And finally, it saves all of this into an array map to be able to check it at runtime afterwards. And this is mostly convenient to use an array map because, so I'm making it read-only, but you can read it from user space. So when you're debugging, you're trying to find out what happened and which state was an issue. You got all of this information just available to you in the BPF map. So let me show an example. So here I'm going to show a small example of that looks a little bit like what we had before. So R2 is pointing to the stack. We're going to use that to make to spill -44 into the stack, and then we're going to read it back again. We're going to do a call to a helper. This is just to get a printing point for the test oracle to work. And on the side, I'm showing the BPF output for this. However, it's the BPF output from a little bit ago, so from more than a year ago, when we used to have a bug on this exact logic. So at the time, when you did the spilling of -44 into the stack or any negative value, you would lose the sign information. And because of that, the verifier would think that at FP -40, you've got a positive value. And when you fill it back into R6, you still have a positive value. So there's something going wrong into the verifier. So to show this, I've reverted the fix for this, obviously, and that's what we get here. So what the test oracle is going to do first is it's going to patch the BPF program with some special instruction I've added that allows us to know at runtime when to run the test oracle. So this small instruction is not actually executed by the interpreter, so it looks a bit weird in this sense. And it's pointing to the BPF map holding the states for this specific point of the program. So if we look into that map, in this case, we only have one path through the BPF program, so we're only going to get one state. That state has R0 equal to any scalar, right? So the scalar is unbounded. And then R6 is a scalar that has a positive value for most of the ranges. The S32 range is not affected by the bug, so it does have -44, and then some TNM. Then at runtime in the interpreter, when it reaches this point, it's going to take the concrete values and check that they match at least one of the states in the BPF map. So in this case, I only have one state, so it's going to check that it matches this state. If I had multiple states, it needs to match at least one state. And here the idea is that if we have multiple paths, we know that we're at least corresponding, the concrete values, they correspond to at least one path on all of the different paths. So it needs to match at least one state. When it tries to do this, the runtime value, the concrete value is -44, obviously. So when comparing, it's going to throw a kernel warning because it differs from the ranges in the state it has. So it's going to throw a kernel warning with pointing to the map where the information is and the register that had the issue. Okay, so let me go into some of the aspects that require more thought. So first, the instruction I mentioned. So this is the instruction holding today the Oracle map. It's an LDIMM64 instruction with like a new, basically, I think it's BPF sudo map Oracle code. It feels a bit clumsy because today it's exposing this new code to user space, but it's also maybe not the best way to do this. It looks a bit weird when you're looking at this bytecode, and it's actually overwriting the value of R0, so I don't know. All of this feels a bit like hackish, so maybe we need to change it, either to something that looks a bit more like what we have in terms of internal-only instruction today. We have one for the no speculation stuff. Or we can maybe get rid of the instruction, but that will require a bit more work on the interpreter side. Something else that may need a bit more thought is when we want to run the Oracle. So in the example, you've noticed that I've been adding a new printing point by adding a new call to a helper just to get this printing point. That's obviously not optimal for further. We want to have like the simplest BPF program possible, triggering the bug. So maybe we need something different from printing points. Maybe it needs to be printing points and the exit instruction, or maybe it needs to be something completely different. I use printing points mostly because it's very useful, very easy to do. It's already there. It's convenient. It's already where we save some of the states. So yeah. It's also, the printing points are happening on lots of different cases, as we've shown in the presentation with Mai before. We've gotten potentially a lot of printing points. I'm not sure it's quite useful to check this Oracle state in all of these cases. Then the RFC patch set is not supporting subprogs today. There isn't really anything blocking subprogs. I think it's more that if we do support subprogs, it's going to be, so like the state for subprogs is not going to be indexed by the call chain, so how you reach the subprog. So it's going to be a bit less precise than what the verifier is doing. So basically, we're going to have to store all of the different states for all of the different ways of calling this subprog at the same instruction index. So we may not notice some bugs, but I think it's maybe easier than tracking the call chain at runtime. And finally, we can probably check a lot more than just the ranges. So if we look at what I'm checking today, I have this small structure basically saving the state that is checked. It is saving at the end all of the different ranges plus the TNM. And at the very beginning, I have like a Boolean just to say if it's expected to be a scalar or not. I added another one that is saying basically if it's a pointer that is supposed never to be null. So basically we've checked that it's not null. So for instance, if you've got a map value or null, we've did the check. We know that it's not null anymore. So if at runtime it is null, we've got an issue here. But probably we can do more. Mostly I'm guessing on pointers it would be useful to have a bit more, but it's not obvious how to do more than this. And with this, I conclude. So I've just presented very briefly a test oracle to expose false negatives into the verifier. And to help further do this, there's an RFC on the mailing list. So I'm interested into feedback on this and happy to take any questions.
So, quick question. So, like, do you, so then, like, Oracle by itself is not, like, useful. It's only useful when fuzzing is applied, right?
Yep.
So, did you try actually to, like, run the fuzzer with it and find something?
No, not yet. I haven't. And there's also, so I'm guessing that's probably the next step, right? Would be to just enable it in Syscaller. So today it's kernel config, so I can just enable the kernel config and then run Syscaller with it.
Even before, like, all the discussion, like code reviews or merging or not merging, like it's worth like exploring whether it actually like finds stuff, right?
Yep.
Because the example you gave, it's like technically you don't need the fuzzer for that. Like you can just, I don't know, our BPF verifier visualizer can potentially detect it. Just saying, look, you're storing -1 here and reading, and the verifier says, I'm reading this FFF, large unsigned number. So it could have been obvious to even AI. Like AI can take a look and says, find the bug here. So,
I mean, so in the first case, you need to write a rule saying, I'm checking this exact case, right, in BPF visualizer, which
not
is sort
necessarily.
of...
Like if you go back to the slides, you can just like paste this into AI and say, is the bug here in the log? And I bet that it will find it already. So yeah, my question is like, how useful is going to be like for fuzzers? Because like for this, not this one. Like you just like,
this,
like this. Just copy paste the stuff on the right, and I bet AI will find it. So for this particular example, I would say like aiding all the infrastructure and fuzzing is not worth it, but I suspect like, yeah, fuzzers of course can generate way more complex programs, and then it can be useful.
Yep. Yeah, I think next step is testing it some further.
Questions? All right. Thank you.
Thanks.
It's been
Yeah, I think just use this one.
Yeah, you have to use this one.
Got it. Okay.
Oh, this is just yes or no?
Yeah. Okay, so looks like we're starting early. Yeah. Hello, everyone. My name is Peilin Ye, and thanks for coming to this session. And today I have about 30 minutes to talk about BPF load acquire and store release instructions. So I work at Google as a software engineer, and our team works on SCADX-style CPU schedulers that are based on BPF. So yeah, we have a lot of stuff in BPF. One day I was browsing one of our BPF programs when I saw this. This line does an atomic fetch and OR with 0 on this 64-bit integer, and saves the old value. I was like, okay, but isn't this essentially just a
atomically loading a value in a not so typical way. And there was also a comment saying eventually this could be a load acquire. And I was like, I'm not sure what is a load acquire, but what if I just go ahead and try that? So I looked up the syntax and created a tiny program that simply does this load acquire using a compiler built-in function atomic load n and specifying flag to request the acquire memory order. Then I tried to build it with clone 19 and I got this. Some of you might have seen this before. It's very hard to read, but basically LLVM is telling me that guess what? I'm not sure what is BPF load acquire either. But luckily, that is no longer true because BPF load acquire and storage leads have been out there for a while. You can use them in your BPF source code if your LLVM version is, I believe, 21 or higher. And right now, 4 target architectures are supported. Initially, the ARM64 and x86 64 support was added in kernel 6.15. And RISC-V64 support was added in kernel 6.16. And most of the work was done by Andrea Pari. And most recently, Paranjay Mohan added the PowerPC 64 support in kernel 6.17. All right, here's the plan for today. I'll start with the why part. I'll do a quick refresher on memory barriers, what load acquire and store release are, and what motivated us to support them in BPF. Then we'll move on to the what part, where I'll show the encodings of the 2 new instructions, how to use them, and plus a couple of minor things to note. After that, in the how part, I'll do a walkthrough where we start from the toy program, demo.bpf.c, all the way to native instructions. And in a sense, this talk is intended to be a semi-tutorial. We'll see a lot of examples, and I'll be highlighting things that I personally found interesting or didn't know before I started doing this work. So hopefully you'll find them interesting as well. Finally, I'll talk about potential to-dos and next steps, and I'll try to leave a couple of minutes for comments and questions. So first, some background on load acquire and store release. This code snippet you see here is part of a simple litmus test for the Linux kernel memory model, or LKMM. It demonstrates the classic message passing pattern. So on the top, we have a producer thread that stores some data into the buffer, and it sets a flag to indicate, hey, my data is ready. And on the bottom, we have a consumer thread that loads the 2 shared variables in the reversed order. Basically, it checks the flag first and reads it into the local variable R0. Then it reads the buffer data into R1. So the producer and the consumer run concurrently, and by the end of the day, the consumer is possible to observe different combinations of R0 and R1 values as outcomes. For example, if the consumer is too early, it can see 0 and 0. Basically, the buffer is marked as not ready, and yeah, there's no data in the buffer. Or it can be 1 or 1 if the consumer is very late to the party, and where the data will be ready, and it will be marked as ready as well. There's a tool called HERT7, which can be used to analyze this litmus test and report which combinations of R0 and R1 values are allowed or possible under the Linux kernel memory model. I have the comments here if you'd like to try it yourself. Now, according to HERT7, there's one possible outcome, that is R0 is 1, but R1 is 0. So basically, it's possible for the consumer to observe that the flag is set. Hey, my data is ready, but when we actually read the data, the buffer contains no data. So I grabbed a pencil and paper and found this particular outcome very counterintuitive. Conceptually, it's as if the two write onces in the producer have been reordered or swapped order, or conceptually, the two read onces in the consumer have been reordered. So roughly speaking, modern CPU does this kind of reordering for performance, especially if we're using a relaxed memory model. But as we can see, sometimes we want to avoid this kind of reordering because we want to keep our program correct. So that's where memory barriers come in. So again, conceptually, memory barrier is a way to tell the CPU, please don't let certain kinds of memory operations reorder around this point. For example, if in my program I have a store followed by a load, then by keeping the store load order, I actually mean, or keeping the SL order, I mean that no other threads are able to observe it as if the later load happened before the store. And a full barrier is the strongest form of memory barrier. Where out of load store, store load, and store reorderings are prohibited. For example, if you recall the example we saw earlier, this atomic fetch and atomic fetch and OR with 0 example, that helper actually was an atomic load with an implied full memory barrier. Okay, so a store release gives you store and load store ordering. It ensures that loads and stores before the store release won't be reordered to after it. And similarly, on the other hand, a load core gives you load store and load ordering. It makes sure the loads and the stores after the load core won't be reordered to before it. So if we use them to fix our litmus test example, for our producer, we can make it set this flag value using store release to make sure that it's ordered after storing to our buffer. Roughly, only publish your buffer when it's actually ready. For the consumer, we make it read the flag using load core to make sure it's ordered before loading from the buffer. Roughly, please only consume the buffer after you've checked the flag. So after the changes, counterintuitive outcome we saw before becomes no longer possible. Actually, this is another litmus test available in the kernel source, which you can check out as well. So yeah, sometimes a full memory barrier is too strong for what we actually need for correctness in the code. And as long as the code is correct, using load core and store release instead of always defaulting to a full barrier can be better for performance. And since load core and store release still allows some reordering, and this became more interesting as we started looking at running our BPF code on ARM64 because it has a more relaxed memory model than, say, total store ordering of x86, 64. So ARM had the potential to benefit more from being able to use load core and store release directly in BPF instead of defaulting to full barriers. Okay, so let's move on to the world part, which start with the encodings. Both load core and the store release instructions are encoded as STX atomic instructions with the immediate field or in field to indicate which one it is. For load core, the immediate field is 0x100 and 0x110 for store release. Here's a concrete example of a 16-bit load core. And yeah, you can take a closer look if you're interested. Basically, the 0xCB here is a opcode, which can be broken down into different fields that I used a different color for. One thing that could be interesting is the SZ one, which is a size modifier, indicates that it is a 16-bit load. All previously, all atomic instructions that previously existed perform read, modify, write operations, for example, fetch and add or fetch and or. On the other hand, of course, load acquire is a load operation and store release is a store operation. Another difference with existing BPF atomic operations is that they only support 32-bit and 64-bit mode, while the load acquire and the store release support all size modifiers, basically 8, 16, 32, and 64-bit. Also, load acquires are zero extending if it's a subword. For example, a 16-bit load acquire loads a 16-bit value from the memory, and zero extends it to 32-bit before saving it into a 32-bit wide BPF sub-register. But we'll talk about more on sign extension later. Usage is actually pretty straightforward. There have already been examples in earlier pages. One thing to notice is since load acquire and store release are v4 BPF instructions, you want to use this -mcpu equals v4 flag when you compile to allow a clown to generate v4 instructions. And while we are here, there are actually 4 more __ atomic flags defined in addition to acquire and release. So I'll go over them briefly. If you use relaxed, these just become plain zero extending loads and plain stores. The second one is consume, but in LLVM, this one is actually effectively treated as an alias to acquire. So let's not worry about it for now. Acquire plus release, this one is illegal for atomic load and atomic store helpers. Finally, we have sequentially consistent, which isn't supported yet. If you try to use it for atomic loads and stores, clown will error out and tell you it's not supported. I tried to make this error message shorter, but yeah, it's still pretty long. But it will explicitly tell you that it's not supported at the moment. And yeah, just for completeness, I also included inline assembly examples. This one is a 64-bit load acquire. And another one is a 16-bit store release. So one small gotcha to keep in mind for inline assembly is that when you are working with 8, 16, or 32-bit values, you will want to use this W input or output constraint for sub-registers instead of R, which is for the 64-bit wide whole registers. A couple of notes. So arena access is supported just like existing atomic operations. Currently, ARM64, x86, 64 were initially supported, and the last time I checked, RISC-V 64 arena access was also supported. And for portability, you can use this ifdef on this predefined macro to detect whether your compiler version supports the BPF load acquire and store release. And maybe potentially fall back to something else if it doesn't. I'm not sure if it means to falling back to fetch and or with 0, but yeah. All right, that concludes the second part. So as promised for the next section, let's take a closer look at how this is all implemented. Again, here's our toy program, which is a 16-bit load acquire. And when I started this work, my mental model basically looked like something like this, the big picture in 3 steps. We compile the C code into an .o object file containing BPF instructions. And then we load into the kernel where the BPF instructions eventually become native ones. Pretty straightforward. But of course, there are several intermediate substeps along the way. For example, during the compilation process, there are actually quite a few stages before you can turn your .c file into a .o file. The first one I'd like to briefly mention is something called LLVM IR, or intermediate representation, where LLVM first turns our C program into an internal form that looks like this. This page is mostly for completeness, but one thing to note is that this step is supposed to be backend independent. It doesn't have much to do with BPF yet. And this is a .ll file. And if you take a look at the command I used to generate it, you can see that I didn't even mention BPF here because, yeah, it's target independent. So next step, LLVM takes the .ll file, then turns into the graph called the selection DAG. I said graph because it actually is a graph that looks like this. I didn't know. I found this selection DAG thing pretty cool. It's used for a process called instruction selection, or ISEL. And it happens in a sequence of mini steps where each mini step take a selection DAG as input and does some process and produce a new one as output. So this graph actually represents our simple toy demo program. And right now it is still target independent, but we're just about to translate it into another DAG containing BPF instructions. So if you zoom in, the biggest node here is actually the most important one for us, which is our load acquire. And this is exactly what that clam19 huge error message was complaining about. Basically, it's saying that I want to translate this target independent selection DAG node into BPF instructions, but I have no idea how to do that. What's happening under the hood is the LLVM BPF backend maintains a bunch of target description files, or the .td files, containing information about how to map selection DAG nodes into BPF instructions. And using those TD files, LLVM uses an infrastructure called TableGen to auto-generate a table called the matcher table. So when we try to translate that node, that load acquire DAG node, into a BPF instruction, we do so by looking up the matcher table. However, for older clown versions, nothing matched. So compilation process had to fail, and thus that big error message. Therefore, what we needed to do to support load acquire and store release in LLVM was to modify those BPF target description files to teach LLVM how to translate or map that load acquire DAG node into BPF. If you look careful enough, someone may ask, by the way, this node looks like it's Zext or zero extending, but how about sign extending? Because I know, as a fact, that for plain loads, we have both versions. We have the zero extending plain loads. We also have sign extending plain loads. So why not have sign extending load acquire as well? There have been discussions during the review process of LLVM pull request. But unfortunately, as it turns out, the way that LLVM is engineered, it expects a platform's atomic operations to be one of zero extending, sign extending, or undefined. So for example, for ARM64, it's zero extending, but for RISC-V, it's sign extending. So I tried, but it turned out to be at least non-trivial, if not infeasible, to have both zero extending and sign extending BPF atomic operations. So right now, we are just defaulting to the zero extending behavior for BPF. If you're interested, you can take a look at the usage of this LLVM function called get extend for atomic ops. Okay, the second half of the journey, which is in the kernel, might sound more familiar to you. The main responsibility of the verifier, of course, is to verify the program before the per architecture JIT compiler, just-in-time compiler, can finally compile the program into native instructions. So for the verify part, two rules I wanted to highlight that we enforce for load car and store release instructions. So first, unaligned load car and store releases are rejected. Even if we have this flag we can set called any alignment during the load time. Even if we set this flag during load time, unaligned load car and store releases are still rejected. So this is mostly for guaranteeing atomicity because, for example, a 4-byte plain load on x86-64 is only guaranteed to be atomic if it is aligned. And the second rule is we reject 64-bit load cars and store releases on 32-bit architectures for similar reasons, also for guaranteeing atomicity. So let's talk a little bit about JIT compilers. So for ARM64, the JIT emits LDAR and friends for load car and STRL and friends for store release. And it turns out in the ARM world, we have two flavors of load car instructions, namely RDAR and LDAPR. The LDAR provides an ordering semantic called RCSC, which is stronger than the ordering provided by LDAPR called RCPC. So the BPF load car instruction itself is defined to have RCPC, the weaker semantics, but the ARM64 JIT actually implements it using LDAR, which promises RCSC, which is stronger than RCPC. There have been discussions about this on the mailing list, and if you're interested, please reference the email links I have here. Paul McKenney had a very nice summary about this topic. So one reason was simply that since LDAPR is a newer instruction than LDAR, if we let the ARM64 JIT compiler to emit the newer one, it might not work on older platforms. So that's one of the more obvious reasons. And for x86-64, it's a bit of a simpler story because under total store ordering, the load store and the store reorderings are already disallowed, which means that the ordering requirements of load car and the store release are already guaranteed. So long story short, for x86-64, we just emit plain aligned loads and stores. For example, move ZBQ for 8-bit load car, the Z part because it's zero extending. To wrap us up, here are some potential to-dos that I list here. So right now, again, 4 JITs support the load car and the store release instructions, and we can support more architectures. And both load car and the store release are implicit memory bearers, meaning first it's a store or load operations with implied acquire or release semantics. So it also would be helpful or useful to have pure or explicit barriers that, like the kernel SMP, MB, and friends. And there have been discussions to implement those as BPF fast call kfuncs. Also, as far as I know, GCC doesn't support them yet. And as mentioned, the sequentially consistent flag is not supported yet for LLVM. And so far, we've been talking about memory bearers, but what about compiler bearers? Like, as I understand it, currently the JIT compilers convert BPF bytecode into native instructions in a kind of a linear or one-to-one way. So currently we don't worry too much about the JIT compilers reordering instructions, but I think it will be still interesting to have a way to prevent or get a guarantee that JIT compilers won't potentially reorder instructions. Finally, we have for the -MB CPU flag, we have this auto option, which automatically detect which BPF instructions are supported by the running kernel. But I don't think it supports v4 yet. So that's one more potential to do. That's about it. Thank you for listening. Any questions or comments?
So I was wondering why these instructions got lumped in with ISA v4 instead of making it like a new ISA v5 generation. So
I'm sorry. Could you repeat the question?
Yeah. So these instructions were lumped in with ISA v4 instead of making a new ISA v5. Do you know why that happened? It was an interesting choice because the ISA v4 was originally added in 6.6 for like long jumps and a few other things, which makes it interesting because if you now enable v4, then you have to do like probing and other tricks at load time to ensure that your ISA v4 code can run on multiple kernels, right? So I was wondering why wasn't a new ISA? Why didn't we go ISA v5 so you can enable instructions separately during compilation?
I see. I'm sorry. I don't think I get the part when you mentioned could you possibly rephrase the question again, or does anyone else want to take it?
I think I can answer this question. And so basically, we don't want to have too many versions. And then if you have one feature, and then V5, V6, V7, now we already with 11 or something, right? That's too much. So we try to consolidate and with a group of that. And we also have features. And you know that, right? He mentioned there is a macro there. And this feature actually can detect whether this is available or not. So in the long term, and we try to use features and recommend to use features to detect whether feature available or not. Yeah, no. And so basically, yeah, still, we do not want to have too many versions. That's a whole thing.
I see. So initially, this was proposed to be added as a V5 instructions, but after some discussion, they were added as to the V4 family. Yeah, and we have predefined feature macros to detect if your compiler support them, and we also have LLC options to explicitly disable those instructions if you don't want LLVM to use them. Yes.
Hi, thanks for the talk. So you've talked about load acquire and store release instructions. Are there any efforts to extend this so that you could apply acquire release semantics to read, modify, write atomics, such as compare exchange?
I see. Do you mean, so currently we support acquire and release to atomic load and the store? You mean, is there a plan to support other orderings for other atomic operations?
Right, yeah, such as compare exchange, for example. Like you might want to say compare exchange release. I just wonder if you were going to, if there are any plans to do that in the future.
Currently, no.
Okay.
But yeah, I would see it would be useful if we support them. So right now, the most usual pattern we see in our code base is load acquire and store release, but we had to stick to full barriers. But yeah, I would see your proposal be useful.
Okay, thanks.
Thank you.
Is the CPU auto something new, or is that working in Clang already?
Last time I checked, I haven't checked this for a while, but last time I checked, it worked for V2. I'm not sure if it works for V3, probably not for V4. So the way this -m CPU auto thing works is during compile time, it creates a test program containing, for example, v2 instructions and try to load into the kernel. If it doesn't, the element will be like, okay, the kernel doesn't support v2 instructions.
Clang does that? Okay.
But right now, for us, it's kind of lower priority because the environment we compile our BPF program is almost always different from the environment we actually run the program. So yeah, but it still confused me a little bit when I played with this option. I think maybe it's because in V3 and V4 we have a lot of new instructions, so it'd be non-trivial to write that test program to load into the kernel.
So I just wanted to add about the question about compare exchange with release and acquire semantics. So in the Linux kernel, all the atomics which return a value, like add with fetch, are already fully ordered. So I'm not sure if there is a use case where we want to make compare exchange weaker. And yeah, I think there are versions implemented in the kernel, but when there is a use case which appears in BPF, I think it's better to only then implement a new instruction.
I was just asking if there were any kind of motivation given was performance.
Other than that, I had a question about the implementation of this instruction with RCSC instructions and not RCPC, because there is no standard right now about which instructions to emit, and I think some
I'm sorry, no standard for what?
Standard about which kind of instructions to emit by the JIT, so RCPC or RCSC, because
Yeah.
I think PowerPC is emitting the weaker, and that would mean that a BPF program can show different behavior on these two architectures.
Are you saying that if we decide to make ARM-JIT to emit the stronger one, they will?
Then we should make every JIT do the same. No, I mean like making it stronger but not weaker than ARM64. Either stronger or at the same level of ARM64, not weaker. Because just because LKMM because right now there is no final form of BPF memory models. Yeah.
Yes.
Just to pick up on that, I think the BPF architecture spec says RCPC, a backend can always implement something stronger, right? So I think what was presented is absolutely fine. And I also, it's worth bearing in mind, right? Even if you used LDAPR, there's no guarantee that the CPU is giving you the relaxed behavior. It could implement, SC under the hood if it wanted to. So I think the way round that this is per the slides is the correct way to have it. And similarly to my previous comment about remodify writes, ARM64 remodify write instructions, although they have, there are versions which are acquire and release. The acquire there is always SC. There are no PC acquire RNWs on ARM64, which I think is a motivation for the backend to treat load acquire as SC. Because if you do implement RNWs later on, it would be quite strange to have the backend emitting two different types of acquire.
Thank you. Yes.
So this is kind of a general question. I'm vaguely familiar with how you can implement a mutex with compare exchange. Can you implement a mutex with this?
I'm sorry?
So like one of the reasons for implementing atomics in general is to allow for concurrent access of kind of surrounding data. Is it possible to implement a mutex with this like load acquire thing?
Is it possible to implement a mutex using load acquire and store release?
Yeah. Yeah. Okay. Thanks for the answer. Yeah.
Thank you. Yeah. Anyone else? Thank you.
So, yeah. Sorry. So now we have a long lunch break until 3 p.m.
Don't actually care about it. Okay. I'd have to look at the code. But got it. Can you have current access to apps?
this. Most of the philosophy of because having itself, right?
Sure.
So it's hard. I find so
right. I mean, the
mutex probably you will have a shape and you have a map element. And in that perspective, for what we are doing, you can compare it and all and string and it out and right it will switch something in, something else will try and then we will get value. Something else out something.
Right,
So
right. But BPF doesn't emit compare exchange at all.
Oh, BPF have a compare exchange.
Okay, I guess I don't know.
Instructions.
Got it.
Exchange instructions. You go to basic. I'll go to verify. Yeah, so
It's definitely possible.
Yeah, so there's no mutex. Fundamental instructions. If you want to construct a new construction, and there is a exchange, the link to some. For the programs, right? Okay.
Thank you.
Sure.
Some of these words. I took one class on this 10 years ago.
Wait, none of these are.
Helen got a tennis elbow. She ran a conference in Portland, and she did all the chairs. Tennis elbow sounds funny, but it's actually like her elbow was messed up for like 3 months, you know. So she had to actually just take like a month off of work. Also, she got hurt. It wasn't anything as long as that was 2 years ago. She's older now. I actually was looking. For me, on your side.
All right, everyone, welcome back. Yep. I will just check the mic too.
This is the mic I have you.
Yep.
All right. That's fine. Very bright here. The most interesting session after lunchtime is talk about cryptography and signing, just so that you can all sleep nicely. Should we start? Okay, so we've been having a bunch of discussions around signed eBPF for multiple years now. Fortunately, there is more that has happened since we last talked, and there's code that actually exists upstream, and you can do eBPF signing. But that's just basic infrastructure support. We need to tie the story together and see how eBPF signing would work in a real distro or for real use cases. Sorry, 1 second. Too much coffee. So first, we discuss why do we need to sign programs. Just a recap, right? Signing is a way to do an integrity check on the program, like is this program okay? And then who is the entity that is vouching for this program? So provenance of the program is a fancy way of saying it. And then using this information, you can do policy enforcement. You can say that programs that come from these and these entities are the entities I trust on this system, right? And then you can build more complicated logic. Some of this we talk about today. I do want this at some point it turns into more of an interaction, because there are some things I don't know where we should go and how we should implement that. But a recap of where we are. Programs with stable instruction buffers, these are your programs that don't have any core relocations or helper calls. They can be signed directly. You can put the signature in the BPF attribute. There's a new member there that's called signature, right? You can pass the keyring that is going to contain the verification key in the kernel that'll be used to verify the signature. The signature is a detached signature if you from a crypto purity standpoint. Programs with the signed loader, this has been the most contentious part of the whole story, right? Like they have relocation, so the instruction buffer that you pass is not stable. So if you sign that instruction buffer in a build server with your private key, libbpf is going to change the whole code, or a loader is going to change the whole instruction buffer before it passes to the kernel. So when the kernel does an integrity check or a signature check on the hash of this instruction buffer, it's not going to verify. It's going to be like, it's not going to work. So thanks to some of the work that Alexis and others have done for a while now, we had this program called a loader program. It's also, we refer to it in multiple ways. It's a meta program or a trace program, but it's actually a whole trace of all the syscalls that the eBPF program does. Programs today are not just instructions, right? There are a bunch of things that come along with them, map operations and everything. That is encoded in this trace program along with a metadata map. The contentious part here is that we don't want to bloat the BPF UAPI with adding random fields just because we have this limitation currently. So we've added like generic signature support. We entrust the loader and say, hey, I'm going to trust whatever this loader does. And the loader has inbuilt the hash of this metadata map, and then and it's responsible for checking the hash of the map and the contents of the map. We had to do a bunch of stuff here. If you look at the documentation on the patch series I sent out, there is a thing we needed for called exclusive maps, which ties the map to the program that is the loader program, so that nobody else from no other privileged program could mess around with the map. But this is there. I'm not entirely happy with light skeletons as they exist today, but that's because the use case did not exist to use them. This was the use case that puts them in the limelight. So we have a bunch of work to do on light skeletons to get them on par with the real skeletons. The ultimate policy, the dream here that every program on the system is provenant. you can implement this very simple policy by on the BPF LSM hook and say that if there is no signature, permission denied, right? Great. If you do this on a system today, it won't even boot because even systemd is loading a bunch of programs and they're not currently signed. So the ultimate policy has a lot of limitations, right? And not just systemd, not only your system will not boot. The real use cases that are using eBPF today will break. So Cilium, another key user, right, it generates eBPF programs dynamically at runtime, and this doesn't sort that use case out. BPF trace users don't even write BPF programs there, and they write scripts. So how is signing going to work for them? The problem I mentioned before, right? These dynamic relocations, they need the light skeletons. Light skeletons there's a lot of work that has gone into the actual BPF skeletons, but the sort of drifted away, and we need to bring it back somehow. Otherwise, it's hard to use light skeletons. The reality today is that the policy needs to be much more nuanced than what it is today. So what's the policy, right? Started collecting a bunch of historical information on how we've done trusted execution, right? Modules, load pin, right? Before I go anywhere into this, I just want to clarify what a loader is. This is not loader BPF programs. It's a user space executable binary that loads an eBPF program. Any binary. BPF trace is a loader. Cilium is a loader. When you write like BPF tool is a loader. So we're just talking about those user space binaries that are loading eBPF programs. And I have a repository that I share at the end of this to get some of this all together, pieced out. It's not fully implemented, but what should a policy look like on a real system? So one thing you can think of, this is inspired from load pin, is that you take either with BPF preload, which is a BPF program that is embedded in the kernel itself, so you can sort of attest it with the kernel image, put it in secure boot, whatever, right? Or that's, to me, that is a little bit too much. So I just loaded it in with the systemd unit that starts as soon as BPFFS is mounted before any eBPF program is loaded. So that eBPF systemd unit is checked as a part of the project. And what you do is you effectively tie it to the dmverity digest. You say that there is a root hash of the dmverity root partition, right? And I have a helper kfunc that I wrote to get this implemented. We don't really do the signature matching from the dmverity signature here. We just do the digest because in theory, your system shouldn't boot if your dmverity signature doesn't check out. So I'm just using hashes. But you can extend it to actually getting the digest of the dmverity partition and seeing if my eBPF verification key trusts this partition as well. So then you can say that eBPF programs should be loading from only this dmverity signed partition that I've signed with my key. There are many other partitions in the system. I don't care about them. I don't want to maintain a manifest of hash signatures. I will just use a signature check. I think this sort of scheme works, like the trusted digest manifest works good for dmverity because there are not so many partitions, right? But it sort of is complicated when you use on a per executable basis if you have to say these are my loaders but I think we can extend it to signatures as well. The problem here is that if you do the wrong thing here, you're going to end up trusting a Swiss Army knife loader. BPF tool is a part of your rootfs. If you say that I am going to trust any loader on the rootfs partition that is also BPF tool, right? You can load anything unsigned. And that's not what we want. But in images which are very minimized and locked down and consciously chosen for a particular use case, where you don't have a bunch of dynamic stuff going on, and there are use cases that follow this pattern, I think it becomes much more simpler than dealing with package management and fsverity or dynamic extended attributes. It's like a clean approach to trusting loaders here. All right, simple sort of code that is a part of this. I will probably send this upstream. I think it's worth having anyways, the dmverity digest to do this. And that's a mistake on the slide, but that's the ultimate policy on top, that if you have a signature, right, like you should, ignore that. Then we have the next case, right? Now, you cannot bake everything into the image. You want to bring in executable content to the image, to your operating system, either a container that is pulled from Docker, right, or a package you install and you're updating stuff, right? You don't want to reboot your operating system every time you want to change something that loads eBPF programs, right? And this is where I think there is already self-tests in the kernel that implement this. We just need to elevate that to a real policy mechanism. Build it into package managers and in distros and people who want eBPF signing. Now, what you can imagine is that package manager, they sign the loader program off host, and they store the signature in an extended attribute on the loader, on the file system. Now, when you deploy this, right, you deploy it in a way that the extended attribute doesn't get destroyed. If it does get destroyed, you recreate the extended attribute on the thing, where with another trusted component of the package management stack on the operating system. But I was able to do this with just rsync, right? Rsync has a mode where it can copy this extended attribute. This is again like this PPF trust shell script that I wrote is checked in there, and then you copy this loader there, and you say fsverity enable, and then you extend your LSM policy program that says that if the loader has an extended attribute, you fetch the digest, and this digest can come from, you can calculate the raw digest by bringing in the executable bytes right there in the BPF program. Why would you do that? You can get the hash from IMA, you can get the hash from fsverity, right? And you can check if that signature that is in the extended attribute verifies against that digest. And if it verifies, you allow unsigned BPF loading for that, right? So this is how you enable use cases like Cilium and others. But that's not like, if I'm a purist, right, and I still am not happy with this. So I go and I say that, no, I really, really do want every program to be signed on the system. And there is a way to do that. It gets more complicated. Some of these ways are, I have not yet implemented this, by the way. I did figure out how to implement it, but the crypto started interfering with my sleep here. So here what you do is you have a root signing certificate that says, hey, KP trusts these programs to be loaded, but can I give this trust to maybe somebody else like Alexei, right, on the machine, but without sharing my certificate. So what you do is when you're sitting together, right, I sign Alexei's key, private key. Alexei generates a key pair, and I sign Alexei's key pair, private key, with my key, and I say, hey, you are the delegated entity now, and you can sign on my behalf. And then, in this case, Cilium would load the delegated key in its in the keychain. This keychain only grants access to trusted loaders. So all your fsverity stuff you built in would restrict this keychain to be accessed by any other untrusted loader. So you get access to the key, you pull out the key, you sign the certificate, right? You pull out the certificate, you sign your program using that certificate. And this is a private public key pair. Both exist on the end system, but if this key gets stolen, your root key is not compromised. So that's the benefit of this approach. I'm very fuzzy about the benefits of this because you still have the private key on the system that can sign BPF programs, right? But for a purist, this still works. You can technically destroy the private key after your program signing is done and only keep the verification key in the keychain. That's one thing you could do. So it reduces your attack surface after the signing and all that is done. So yeah. I think the more sort of Cilium-like use case, the way you can build signing around that is Cilium creates a delegated, is deployed in Kubernetes somewhere, right? The container workload. This creates a private public key pair like a signing certificate on the client side. It talks to a CA entity somewhere, authenticating, wrapping this, encrypting this certificate with application layer TLS using a Kubernetes credential. And it requests for, like, based on its own identity, hey, can you please sign my certificate that gives me permission to sign eBPF programs now. So the CA then signs the certificate and sends it back. Cilium then loads its programs using this delegated certificate that it gets back from the CA. Here, it can actually destroy everything, right? It can just load the verification keys into the keychain and then destroy the private key so that there is no signing that happens afterwards. And then your like real dream policy of every program on the system should be signed still holds true here, right? So I think this is more practical for a cloud native approach, but you do need a CA of some sort. So you need to integrate with this here. I didn't get to implementing this either. So this is my sort of use case where I would like eBPF programs on distributions and end users to obey the principle of least privilege, not require, I introduced this concept of, now we had trusted loaders, right? We trust these binaries to load eBPF programs unsigned. Everything else can load it signed. There is a concept of safe programs. And I think ever since we've had Spectre and Meltdown and all that stuff, we've just given up on unprivileged eBPF because you can craft, no matter how much we patch, like red pollines and sort of PHI and everything in eBPF, they just keep coming. And we've given up on eBPF being unprivileged. But with signing, you can say that, hey, this program is actually not a side channel gadget. It doesn't have security issues. And then do we really need to then elevate capabilities for this? Can we drop some of the capability checks? I then went back and reminded myself about all the LSFMM BPF discussions with Christian and others there in the room, that capability checks are gospel, right? And we cannot give them up. And then we had to implement the BPF token system to sort of work around that by creating a namespace. I think we should discuss this again, because if we could do like something, I wrote the pseudocode there, which is like PPF capable, where the capable check is wrapped either with an LSM hook, where you say like, where you implement your signing verification logic that I've signed this with a special key that allows it to be loaded unprivileged. I allow it, or you go ahead with a capability check. For security folks, if there are any here, I see James, but I don't see Paul. I don't see others. Is this something we could do? Because it would make the story much simpler. And I don't need to do set suid binaries and like give the loader any special capabilities. I don't need to give the user any special capabilities here. And then you can create tools with the special signing key that people can run with principle of least privilege. More discussion?
Paul is not here.
Yeah. Oh, sorry.
Yeah, so Paul Moore is not here, the LSM maintainer, so he would be the person to engage in this.
Yeah, I think that this is worth. I will try to propose this, but it's worth a thought. Otherwise, the next alternative is I had a look at the BPF token code, and yeah. So I think tokens are very powerful, right? Like they effectively work around this limitation. They give you the capability, right? Like it obeys the capability model that you do have the capability, albeit in a user namespace. So you unshare that namespace. The handshake there and the infrastructure involved is quite complicated. So I think it works in a container environment where you naturally running in a namespace setting. But if you want to, on an end user operating system, do you really need to unshare a namespace and do this? I don't know. Like I wish we could get around the capability checks and implement that. Andre, like this was completely shot down in this approach that we have back in here. Yeah.
Does somebody have?
I had demos of this.
As far as I remember, Christian Browner just didn't see the use case for allowing token to be used in the root namespace, and so he didn't want to allow that. But if we have some good use case, I think we can just remove like this limitation that token cannot be used in root namespace is completely artificial, right? Like we can drop it. There was just like no use case, no need for that. And
but what I saw is that it checks basically that where you are mounting the like you create a new BPFFS mount, and you check the super block namespace that created the mount and your capabilities on that. Now, if I'm an unprivileged user and I check my capabilities on the root namespace, I won't have cap BPF. That's where so I removed that restriction where the token could be used in the root namespace. But the check that actually fails is my permissions with respect to the BPFFS mounted in the root namespace. So I still have to set up the delegation somehow in a new namespace where I have cap BPF. So it boils down to the discussion of like.
So how do you create forget about like namespacing and all that stuff. Like how do you, who will be allowed to create token?
So
like to not create the token, sorry. Who would be allowed to create the BPFFS instance that would allow creation of the token? Because that's how it works, right? Like you have BPFFS instance that has like those delegation rights, right? And then like the user space application will open it and then like create token from that.
So the way I implemented it was that any user space application would do that. Any unprivileged user, you put a check in the BPF load code that once or BPF LSM layer, once it tries to load a program that has signature that is signed with a special key, only then will it be allowed to use that token-based loading, right? So token creation and everything is allowed for everybody. The token delegation is set up in a way that it can only load programs, like loader programs, for example, with BPF proc type syscall, right? Nothing special, just one delegation for loading the loader program. And then that signing verification on that side prevents anything from happening with the token. So you open up the token to everybody, or mounting the file system to everybody. But then you have to unshare user namespace as an unprivileged user and do that dance. So the way I implemented this currently was that I have this systemd unit that has a socket, and then you have a library wrapper around BPF prog load. Then you send this, you effectively do this fs open BPF, and then you send this token to the BPF systemd socket, get this back with delegated privileges, and then you load the program there, and then you have the LSM layer that verifies the check. But really, this stuff for what you could accomplish with not having capabilities are not even useful in a meaningful way in Linux anyways today. So we sort of attaching ourselves that cap BPF is required whether in a namespace or not. I don't buy it. I question this, and I'm okay implementing this, but also want to fight for the other thing. Okay, I wish I had paid more attention back then. So I supported you more there. Yeah.
So you were talking about kind of extending the load pin mechanism to help with the loaders. So I wonder if you've looked at IPE, the Integrity Policy Enforcement LSM. So that was something we designed specifically to kind of generalize load pin, so that there's you can have a more expressive policy about what's signed on the system, and it hooks into the various binary calls. So I was just wondering if you had looked at that, or would suggest.
Yeah, I did not. I just looked at the digest that is there. I relied on the IPE to verify the signature before the partition is allowed to be, file system is allowed to be mounted, right? Yeah. So it verifies, and I'm trusting that IPE is verifying the signature. So I'm not doing a signature check against the digest of the block, like blockchain.
Yeah.
But yeah, I'm relying on it implicitly. I'm not building on top of that.
Okay. Yeah, so it was actually specifically designed to extend load pin, so that it may be helpful. It can support FS Verity and DM Verity, but it's got an all or nothing kind of switch at the moment as well. Either binaries are all required or not, but where there is some work underway to add more selectors, policy selectors to it.
I know one of the Microsoft use cases that I think we should eventually pay more attention to, because you want effectively BPF becomes here a very key part of your secure boot stack, right? You've until DM Verity, right? You've mounted the file system and you've extended the TPM state potentially with the kernel measurements and stuff, but you want to extend it with the DM Verity stuff, and then maybe you're loading more eBPF signatures after in early boot that are not a part of the DM Verity partition. They're trusted loaders. So I was thinking something like Leonard suggested. We've not implemented this yet, but you could extend the TPM register, have an API in eBPF, right? That could extend this TPM state with the measurements of these signatures as well, and then you have at the end of the boot stack you could check, is all this BPF policy program that I rely on for my system to be secure, is it loaded correctly or not? I think that would be also something we should build on top of this.
Yeah, definitely. You're measuring and testing the BPF.
At least the first policy program that you have, like that has all the DM Verity and FS Verity check, that should be a part of the TPM state itself. And then you can say that my system is booted securely now with all the policy that it requires. All right, I think that's all I got. I had some demos, but the big blue, green, yellow button is complicated too. Thank you.
Thank you. Hi, everyone. My name is Liam Weishart, and I'm going to be talking about BPF Jailer, a new LSM we've written entirely in BPF at Meta. Let's see. There we go. Okay. So yeah, I'm going to talk about sort of our general architecture, some of the things we're using this thing for. I'm going to talk about some of the issues we've had working with the file system in BPF. I'm going to stop there for a discussion, and then if we have time, we can get into signed binaries. So, excuse me. Yeah, so we created BPF Jailer to sandbox untrusted workloads at Meta. It's become sort of a Swiss Army knife. It's being used for a lot of different things. It can both jail workloads and also allow kind of have higher levels of privileges as opposed to just lower. And we've deployed it across, at this point, most of Meta Infra in a couple different ways, which is what I'll get into. So the reason we had to roll this out was because, so love it or hate it, but my team was responsible for removing the last SE Linux deployment at Meta because of severe performance issues we had with it. We looked at AppArmor and Landlock when we had these new jailing use cases we needed, and we had extra features we wanted to add. We had sort of different ways we wanted to run things, so we wound up rolling our own. It wound up being a kind of a pretty comprehensive set of features we built out, and we really liked being able to work with BPF because, at the end of the day, with BPF, usually you wind up only hurting yourself if you make a mistake, right? We don't have to worry about kernel panics, anything else like that. You never had to upstream anything. Yeah, we haven't had any performance regression. So we have measured performance on a variety of different workloads, and we've measured no regression. I mean, we are obviously, it is BPF, it is using CPU, but as far as build times and other things I'll get into, we have had no performance regressions. So the original use case that we wrote this for was sandboxing AI generated code. So if you go into your AI chatbot of choice, you ask it a math question, it can't really do math, but it can write a Python script that does math, right? So we wanted to sandbox that. That was our first use case. And we basically wanted that code to be able to do absolutely nothing. So that's what we did. But then we got more use cases, and we had to sort of make things a lot more flexible. So the next thing was for private processing, we run certain things now in a CVM, a confidential virtual machine. And we wanted to prevent people at the host level from mounting attacks against that CVM, since that hardware sometimes has bugs. which would allow you to decrypt the CVM memory. So this is where I kind of alluded to this. Now we're not just jailing things, we're actually kind of having different privilege levels throughout the system and saying, oh, the CVM is at a higher privilege level, you can't access its resources. And then we on to some more things. So for database processes, we had some incidents where with access to those files, we wanted to just stop that. You know, if you're not the database process, you shouldn't be able to access DB files. And those potentially in the last two use cases I both mentioned, you could have someone with root access trying to do this. So we had to leverage the fact that LSM can actually restrict root users as well. And then the last two use cases are both on development environments. So AI agents, obviously popular. We have to allow them to be able to do a wide variety of actions, but limit certain things to mitigate the blast radius. So this was maybe the most challenging thing we're working on now is how do you allow someone to have access to, say, 99% of the development environment, but that last 1%, you know, restrict it. And this thing, it's an agent, but it's still running as your user. It has sudo, it has whatever, right? Permissions. So this is what we've built out over the last year and a half or so. We have, I'd just say, sort of the common set of networking restrictions, you know, restricting access to different endpoints based on IP, port, Unix domain sockets, vSocks, whatever. We also have some experimental parsers in the kernel for DNS and dbus to try to restrict those at the LSM layer. We're not actually using those anywhere yet, though. What we do have and are using, it just a little bit more valuable, is proxying. So using the C group hooks to rewrite connect calls, bind calls, whatever, and redirect it to a local proxy for just man-in-the-middle analysis. And this is really useful for agents where with an agent, you kind of don't care if it breaks your own dev server, but you do care when it reaches out to prod and tries to do something. So in that case, being able to man-in-the-middle all of its traffic, which is what we do, gives you a lot of flexibility in how you kind of control this bad behavior. We intercept exact. We have allow lists of like you can run this CLI tool with these arguments, but not those arguments kind of deal. And then what I'm going to talk about in this talk mostly is the file system level stuff. So we have algorithms for how you can choose what files can be opened or, you know, read, written, whatever, on the system. And that's where I'm about to go into. And then we have some other features too, tamper protection. So, you know, you don't want to be able to, you can't allow someone to debug a privilege process, kill a privilege process, and then signed binaries. I will just mention, yeah, we've never gotten around to implementing anything to do with UIDs or capabilities because we don't use them being an LSM, and a lot of things at Meta have root, so there has never been a point. So yeah, I'm only going to really talk about file system things in this talk and signed binaries if I have time, because the networking stuff is all very well understood, I think. There's a lot of features, there's a lot of support in the community. So I'm just going to stick with what's kind of more interesting, I think, to this crowd. So first of all, the way we deploy this thing. Again, this crowd probably doesn't need this diagram, but socket activation is when systemd holds open a resource for you. When there's a connection on the resource, so in this case, Unix domain socket, it spawns your service, and only then is your service come online and then, you know, serve the request. In this case, BPF jailer is socket activated because that way the BPF programs are only ever loaded when there's something to be jailed. And actually, it serves the request by jailing the targeted process. So it actually sees the PID over ucred and will reach out and jail the process that is calling into the socket. So, and we integrated this with our container scheduler. So any container at Meta can just, with a kind of a one-line change, jail itself. You know, BPF jailer, being a root level daemon, can even enter the container's mount namespace and inject things. There's a lot you can do there. But it is kind of brittle and has some weird edges, right? For one, being socket activated, the first time you call into it, you wound up with some startup time of the daemon. The second time you call into it, it's very fast. So that leads to just some weird edge cases. You also, it's somewhat inflexible to have to integrate with an API that calls a socket. So we did add the ability to just sort of do some path-based approaches where you can just, you know, based on your executable path, your C group path, an X adder, just sort of automatically be jailed with one of various roles. And we're actually working on eliminating the socket activation thing because, kind of like I mentioned, you get some weird spikes and other weird unwanted behavior during upgrades. So the way BPF jailer views the world is as what we call pods, which I know is an overloaded term, but that's what we went with, which is a group of processes that are in a jail or have some privilege, because like I said, later we had to add kind of privilege levels. A pod can contain other pods, which allows you to nest layers of policy. So say you had a role that allowed access to, the entire root file system, but then you had a second role that you wanted to stack on top of that allowed access to only your home directory, right? You could just enroll in both things. And the reason why you'd want to do that is because, say, your container maybe has one restriction, and maybe it's a very basic restriction, maybe it's just a certain file your container can't open. But then your workload within the container, which is, the process that's actually doing the bad, untrusted thing, might have an additional layer of restriction on top of that. So we allowed you to express that where, okay, it's a pod within a pod, each pod has its own role, and when you're that more restricted process, when you try to do something, both policies get evaluated in sequence. We also used it to build an escape hatch. So sometimes you really need one process to be able to get out of the jail for one specific thing. So like I mentioned, the original thing here was socket activation. It worked well for jailing. It didn't really work well for more general host level security applications. So we actually worked on making it function through pinned BPF programs predominantly. And this is where we're moving all of our deployments to in the long run, where when the system boots, you go into initRD. In initRD, there is a service that pins BPF jailer to your BPF file system. Once pinned, the service dies. The BPF programs then persist even after the transition to the normal root file system. And this means that BPF jailer is now always installed, and it never needs to be upgraded because it was part of a NIT. It's upgraded as part of a NIT. There's a lot of problems that just go away, right? In addition, it can protect itself. So now anything that's operating as part of the root, root system, it can't really get rid of BPF jailer. In order to get rid of it, maybe you need to reboot the system, but we actually measure a NIT as part of a trusted boot sequence, so that wouldn't work either. And yeah, one thing I'll just mention though is as part of this whole daemonless BPF space, which does work very well in a lot of ways. There's no way to log, right? We actually log to a ring buffer, and we have a secondary program that reads from the ring buffer and logs things. It would be very nice, this has been proposed before, if BPF programs could directly write UDP messages. And the reason why is that trying to maintain versioning between something that's in an initRD and something that is a sort of normally installed service is really a pain. So just being able to, and it's obviously a vulnerability as well, but the versioning is what I care about. And it would be better if they could just write directly to the network. So this is sort of I think probably most of you get the picture at this point, but we target specific processes, sometimes within a container, sometimes not. And we're restricting access to some resources, maybe all resources, right? BPF jailer can target an unlimited amount of processes. It uses a task storage map attached to each process to tell it, what the role of that process is. And the map that, about how many pods it can have, it's 10,000, right? So, we never have run out of resources. And this is sort of the socket activated flow here. So when we're spawning a VM to run AI generated code, we fork into this shim process, which sort of controls the life cycle of the VM. These are cross VM. And before it will allow full execution into the VM itself, it calls into this socket, BPF jailer starts, BPF jailer creates the jail, returns back to that BPF jailer client little binary and says, okay, ready, you're jailed now. And then the whole flow can continue. So this is, like I said, it's very nice for jailing, and it guarantees that BPF jailer was up and started before you started your workload. So you know you were jailed, and actually you'll get blocked from continuing if BPF jailer happened to be down. But it doesn't work for everything. So, and again, this is kind of what I was getting at earlier. For some cases, we don't want to jail anything. We actually want to have a higher level of privilege. We want to have some process that is the only process allowed to talk to a protected resource. So in this case, being kind of socket activated, all that doesn't really make sense. And we operate through this initRD installation, like I mentioned before. And we can protect that process. We can protect it from being tampered with. We can protect it from being killed. We can protect the resource itself from being accessed by processes that are not, this privileged protected process. And this is what we do for CVM applications. So in this case, you have some AMD hardware that's encrypting a virtual machine for you, and it's keeping that safe. But there are sometimes bugs in that hardware, and we don't want to allow someone at the host level to mount an attack against the hardware and just give them a free crack at it, right? There have been CVEs out there, and we just want to stop that. So what we do is we say there's a specific blessed QEMU binary that's signed by our infrastructure that is the only thing allowed to access these devices. And BPF Jailer then enforces that nothing else can touch that QEMU process, nothing else can touch those device files. And then we also lock down, things like kernel module loading, BPF program loading, et cetera, to reduce the blast radius here.
Couple of
Yeah, you want to say something?
Yeah, but is it okay to ask some questions? Or?
Yeah, go ahead. I'm going to stop in a minute anyway, but you can go now.
Perfect. I was, you had a previous slide, you had cross VM. So is that where you're doing the untrusted sort of code? So you have an outer layer on top of the cross VM that you're implementing. You're not using the seccomp policy that comes with cross VM. You're complementing this with the seccomp policy.
Yeah, I actually don't know if we even use the seccomp policy at all.
Okay.
We use a layer of namespacing and then BPF Jailer on top.
Pretty nice. And this stuff is open source, like.
BPF Jailer, we're going to try to open source it next year. That's the plan.
Awesome.
Yeah. What we will open source is actually this stack. So installing it as part of a NIT and having a bunch of pinned BPF programs is what we'd like to open source. The whole socket activated daemon thing is, I think, less valuable and also has more meta stuff that I have to strip out. So, okay, so file system matching. So this is what I'd like to kind of have more of a discussion about. So I'm going to go through the next couple slides and then we can talk. I think the long story short here is that users there's a variety of situations in which you want to restrict access to files or match files. Maybe you want to enroll certain executables in a jail. Maybe you want to enroll certain C groups in a jail. Maybe you want to allow access to, in this top right example, /etc, but you have some secret directory in there you want to block access to. So maybe you have a hierarchical structure of paths that you need BPF to be able to understand. And people think in terms of paths, right? So I was here 2 years ago and I was told use inodes, right? People think in terms of paths. We did something in terms of paths. I'm not going to say it's 100% the correct approach, and I'd like to discuss with the room, but that's what we have. And what we had to do to represent kind of people have these corpuses of paths they want to match against was create this sort of graph structure, which I show in the bottom right. We had to support some basic wildcarding functionality because container paths, for example, have random elements to them, and you can't predict what those are going to be. We do have a layer of catching. So, we do catch what inodes are frequently accessed, remember what the lookup values were, and then invalidate that catch on rename. So we do this matching with a two-step process. The first step is to extract a vector of string views. So you have to extract all the directory names, and the file name that you want to match against, right? So the first step is to walk up the D entries, walk up the mount tree, and get all of the names. We support up to a 255 directory deep tree, which of course is not enough for some people, but it should be fine. And it takes 2,000 lines of code to do this, which would not be a lot by pretty much any other standard. But for BPF, maintaining that amount of code and getting it to all run inside programs that have other logic on top of this is quite annoying. And we run up against stack limits, instruction limits, whatever, max number of BPF loops that can be nested into every limit we've hit. And the biggest issue, though, that we have here is actually bind mounts. So when you walk up this, this tree, and this is not an accurate picture of what the tree looks like, but this is, for my demo purposes, you have two mounts here, right? You have this home Liam Weishart mount, and that has all my files in it. And if someone was an attacker wanted to open these files and give BPF jailer a different path, all they have to do is create a bind mount. And that bind mount can bind mount over my home directory. And now in red, there is a different valid path to all of my files, which again, if you're doing a path-based matching algorithm, you've now completely thrown everything in the wind, right? How am I supposed to know in BPF what's the right mount here? And this is just one of many ways this can be done, right? You can mount over a mount. You can remount something. We could spend all day talking about the different ways you can do this. So what we did to solve this problem, at least for the most obvious cases, was I think the key realization was that the mount namespace that a process is in is not something that can be trusted, because any process can enter a new mount namespace. And if the person then has any sort of even partial root capability, they can potentially create new mounts or whatever. And at Meta, a lot of things have full root access, and so you really can't trust anything that's going on in that mount namespace at all. So the first thing we do is we jump into PID1, we jump into systemd, and we look at its mount namespace. And we actually build a map of all of the mounts in systemd's mount namespace. And we look at how they connect to different D entries and the different D entry trees. So then when we go into our walk up the D entry tree, we just ignore the mount that's passed in as part of like the struct path. We just walk up and we choose which mount to select when we need to jump between different D entry trees. And we do this based on what's the oldest. So again, this isn't a perfect solution. I'm sure all of you here have your own unique ways to break this. But when you combine this with aggressive enough LSM rules about renaming, unmounting things, hard links, you end up with something at least reasonable. And going back to bind mounts for a second, you actually can't really effectively restrict bind mounts using BPF LSM the way that the LSM hooks are currently written, because directory, and then even once you did that, there could be symlinks in there or whatever, and you wouldn't know about it. So we have to do this kind of wonky algorithm in order to deal with bind mounts. Well, Song Lu has tried. Is he here? I think Song's here.
And?
Oh, he's back there. There. But anyway, it was not accepted.
Why? Yeah.
Sorry, I missed the question.
The question was why can't we add a new LSM hook for bind mounts?
That was a proposal like almost a year ago, and the discussion didn't go well. And we're trying something else. And later, I got a nag over Thanksgiving weekend, and seems the discussion going back to the original direction to have another LSM hook for bind mount. And I don't know how well that's going to go. I think we get okay with either way, but so far is if you count the time of the year, we haven't moved the thing at all. Sure, let's talk.
Awesome. So this is how the actual matching works. Well, this is a little simpler than the way it actually works. But you have your vector string views. And like I mentioned, we needed to support wildcards. We needed to support also a large corpus. We support, for one workload, I think it's 3,300 different patterns, all being matched O of 1 against whatever your path is. The way it works is that every string, so directory name, is looked up in a hash map. That hash map is then, the value there is used to look up two more maps. One is a list of allowed transitions from that state, and the other one is a list of new iterators to push onto this stack of iterators. The state machine just sort of runs, every time you have a new directory name, you look up new states, see if you are either advancing any of these iterators or you're kicking them out because they didn't match. There's a map of wildcards states. So if you hit a wildcard, you just get a free pass to the next state. And then when you hit the root D entry, And again, we want to look specifically for the root D entry because that means you're in systemd's mount namespace. If you can't find the root D entry, if you walk all the way up the D entries, all the way up the mounts, and there's nothing, you're probably in someone else's mount namespace, something that's not even accessible in the root mount namespace, and that's a different situation. So anyway, once you hit the root, then whatever iterators have survived, those are your matching paths, or your matching patterns. And based on what patterns have matched, you can now choose what policy applies. So you might choose, hey, the longest pattern, which would be the one that is the deepest. That might be, that might have the policy you care about. Maybe all of them have policy you care about. It doesn't really matter. The algorithm's somewhat flexible. So this is sort of where I'm about to pause. Yeah, obviously this is difficult. It's obviously slow. I did mention before, we have not observed any performance regressions from doing this, even though on things like, builds or database workloads. But it does show up, right? Like you can see the CPU utilization is there. This is only on open, it's not read-write, but still it's significant. But I think the bigger thing is just that the Linux file system is so permissive, right? And, trying to enumerate bind mounts, okay, yeah, maybe we'll look for bind mounts, but, especially when you're thinking about, what can a root level user do, they can really trash their file system, and having to enumerate the different ways to deal with it it's painful. And then the last thing I'll mention before I stop is that we have to deal with yes, we could use inodes. We do use inodes. So there's a question if you're confused why I'm just talking about something else. We do use inodes for catching. But the issue is that we were concerned about exhausting resources, tracking too many inodes. We rely on allow listing whole directories, right? The other issue with inodes is what happens if someone renames a directory an inode is in? How do you know that directory, that you should block that rename because it contains an inode you care about? And, multiply that by some long directory structure, right? Because we know the path that we care about, we can go up and say, okay, you're renaming, my secret folder, and now you're going to be able to have access to it because it's going to have a different path now. Inodes, and I will also mention that the semantics are sometimes slightly different with what people expect, right? Sometimes there is a specific file and you can say, I want to stop you from opening this file and here's its inode. And sometimes what people want is a little fuzzier than that. So I think it works in some cases and not others. Do you have a question?
Yeah, I mean, I was just thinking, right? If we don't do file-based, path-based stuff, and we just put extended attributes on actual files before you start, allowing untrusted code to run, and then you've labeled all your things sort of SE Linux style for implemented BPF, and then you use that extended attribute information to implement your security policy than anything that is path-based.
I mean, I think that would work. I would be worried about performance there, right? Because now you're hitting the disk for the X-adder values, right?
But you could then transition the X-adder value into the task, or into a map of some sort, right? You could maintain that if you effectively disallow X-adder writes updates after a certain point, then you could, what you do is you build this cache of all the dentry and all that, of the root mount namespace. You, instead of doing that, you build a cache of all your X-adders in a map, and then you don't.
Yeah, no, that's a good point. And we did look at X-adders, and the other thing, we didn't really want to get into the business of policing X-adder permissions, right?
Are they used anywhere, in your?
Not really. I mean, we use them in this for signature validation, but
there are user security and few namespaces. I learned it the hard way from Christian as well, and we could restrict to some of those, right, in which you're using it for this particular case. I think open sourcing this would be nice so that the cases could be made for this. Also having this a part of cross VM instead of the seccomp sandbox, and being it available as a outer layer sandbox or cross VM upstream, even maybe cloud hypervisor upstream would be nice.
Yeah, I mean, this should be compatible with pretty much anything. I'm going to get to one more thing, and then just real quick, because this is what we're not going to move past, I guarantee it. It would be nice if we kind of rethought the way we looked at files in BPF. So my modest proposal here is that you allow BPF LSM programs to redirect open, similar to how Connect can be redirected with a C group program. Because it would open up a tremendous amount of flexibility for jailing and containerization. But I think even, and I'm just throwing this out here, okay? Even if you don't want to go that direction, thinking a lot more about how to deal with files in BPF and the file system in BPF, I think should be looked at, because even doing something as simple as I'm going to make a BPF trace script where I'm going to print the file paths that are opened on my system, it's very difficult. It's very difficult to do, and it's going to be wrong, right? It's not actually going to be a correct solution. So with that.
I just want to, like, I also thought about extended attributes case, but then, like, to my mind, kind of realization, you did mention the init at the beginning and all the hard parts of distributing extended attributes in some file system lineages and initRD as well. So I don't think, like, to pursue the extended attributes case, like, we need better support of the extended attributes in distributions.
So just real quick too, there's kind of two models we're currently supporting, and now we're trying to transition away from the socket activated model. We had to originally support a model where BPF jailbreak is not always running, right? In that case, it can't actually remember anything about inodes or, you know, it can look for X adders, but it can't remember whether it enforced that X adders were, you know, following certain rules, right? Now that we're moving to this init mode where it has always been there since the system is booted, it's a little bit easier to justify things like, okay, well, you wrote an LSM rule that the X adders followed our rules. Yeah.
Be collected at runtime.
So I've basically eliminated pinning maps with this stuff because of the endless versioning issues that we keep running into. Because anyway, that's a different thing. But you're right. Yes, you can keep it in a map.
And regarding the XAtters supported, I understand, like TempFS, for example, doesn't support XAtters. It's painful, but are you restricting TempFS paths, like maybe UDS?
We restrict all paths, any valid path. And with the only one that's special rules is /proc, because we also support like special things around /proc.
I mean, for the last point, right? Like new helpers and hooks, Matt from our side has been checking in a bunch of like helpers, like the acquire release semantics for get MMEXE file. We ran into production issues because it caused like race conditions. It's incremental. Path-based stuff will always be incremental. If you see there is an FSK funcs, so more of those.
Yeah, the issue with the issue is also like, you know, what one person expects when they say, give me the path that corresponds to this D entry is not what another person, like to the point I just made, right? You have to look in different mount namespaces, you know, what could have completely different meanings.
Yeah,
So,
I think we need to pursue the non-path-based system for.
But if you have a non-path-based system, right, how do you express, I mean, people still think in terms of directories, right? They still want to say under this directory, everything under it is protected. And then what do you do, right? And then you have renames and mounts, and you know, you really have to think through all the edge cases with XAtters. I'm not saying you're wrong. I'm just saying you'd have to study it. And
you have to go back and think about how you distribute.
Yes, well, that is the other nice thing about this system is that this is a drop-in, so people can just put in the path they want to protect, and it just works out of the box. So that has been a good feature. So, okay, all right, thanks everyone. There are slides. The slides are up, and they talk a little about signed binaries if anyone cares about that. But you know, this was a good discussion. So thank you.
So how do I move slides? How do I change slides here?
Yeah, you can use this, or you can use the arrow keys.
Okay, that before. Hello, everyone. My name is Carl, and I'm going to be presenting MetaArmor and how we use it to track files across the file system. So this is the agenda. I'm going to be talking about the problem we're trying to solve, then MetaArmor and how it solved that problem, and then I'll be talking about some use cases we have and how we track these files across the file system. So obviously, security is important, and it's becoming even more so. At Meta, we have a lot of data that we want to protect, and we have a lot of actors that want to access that data. And this is becoming more and more of a problem because with AI coming into play, first we have more attempts at stealing data because you have all these LLMs that can create malware, and we also have AI data that we need to protect. So we needed a way to detect and stop these cyber threats in real time, and this is why we were trying to solve the problem. So our solution is MetaArmor. MetaArmor focuses on 3 pillars: collecting signal, preventing intrusion, and then responding to an intrusion. So for signal, we collect like events that happen on the host, and then we log them for like retrospective analysis. We also focus on prevention, where we can emit security alerts where certain things happen or have automatic events, and then we can do a response, either automated or manual. We are also going to focus on integrity next year, where we can ensure that a server is not compromised and it is in the state we expect it to be. And to do that, we leverage BPF very heavily. And the reason is because it's safe, and it's fast and it's reliable. We can also analyze events as they come in and not have to periodically scan like systemd to know like states of things. We also hope to make MetaArmor open source by 2027. The reason why it takes longer than BPF Jitter is because we have more dependencies that we're trying to eliminate next year. So this is where everything starts, is at the BPF layer. We have something called an armor, which is like a user space component that manages the lifecycle of a BPF program. And then the BPF program is linked to a syscall, and then from there we capture a syscall. We filter the vast majority of the events, and the reason is because if you were to log everything, like we would have petabytes of data across all the hosts. So we have heuristics to drop events that we deem safe. So these are usually done by file path, which also have problems, but also IP addresses of services we expect things to connect to, et cetera, et cetera. After an event passes that filtering, we enrich it with further information, like the proc it belongs to, the user that ran that command, like SSH information, and then also some meta context, for example, which container it belongs to. And then after that is done, we move into the rig buffer to then be consumed by the armor, and it moves down the steps. So this is the data flow. So like most things start at BPF, then they go to user space for the armor, and then from there down the line, we either have a response, an alert, and we also log every single event that gets to that point for analysis in the future. In the middle, we have the rules engine, and that is, and we have our own like kind of pseudo language we define in configs to tell it what to look for events. And we do that because we want to be able to update the roles MetaArmor supports without having to do a code change. Because like pushing a code change across all our feet would take multiple days, whereas a config change would take like 10, 30 minutes sometimes, depending on how fast you want that code change to go. So it supports a lot of operations, like we can tell it to look for specific fields. We can tell it to do like regexes on certain fields. And we can also tell it to do things if conditions, certain conditions pass, like response alerts. We try to push as many filters as possible to BPF, and the reason is because it's way faster. We don't need to push things to ring buffer and then get them in user space. So like whenever possible, we try to drop everything in BPF, but obviously regexes and like complex operations need to be done in user space. So this is all the signals we support. So as you can see, like we cover a lot of different syscalls, like some like obvious ones are like process executions. So like when someone forks or creates a program. Some other ones were like binding to a port. We can like know which port it binds to and know who is doing that. And then we have stuff with file system, who opens a file, who sets permissions, and obviously hardware. Someone connects to USB to one of the data centers. This is obviously not. It could be something very dangerous. So there is, yeah, we support a lot of things. We also support a lot of responses. So some of them are very interesting because they leverage BPF. So obviously you can kill a process, but to prevent a process from being like respawned, we also use BPF to prevent that. We hook in BPF, and then whenever we see the same process trying to get respawned, we just prevent it from spawning. We can upload a file, and they are like good use cases for that, and we will see one of them soon. You can quarantine a file that we think is like malicious or that we don't want anyone accessing because it's like it has like elevated permissions. We can gather information, send alerts, and we can also block network access to a process. So how do we use that signal? So this is a cool use case we had a few days ago. I don't know if you guys, many of you guys might be familiar with this, the SHA-1 Hulud malware that affected NPM. So what it did is like when it gets on your system, it would scan for credentials and then upload itself to trusted NPM packages that other people would download, and it would spread that way. So when that malware became public, at Meta we used Mental Armor to make sure it doesn't affect any of our hosts by looking at the logs. And we will, after we isolated the malware, we were able to analyze its behavior, and we noticed like, oh, it would do this syscalls in this order, it would spawn that process. And then with that behavior, we were able to write a rule that prevents that process from ever spawning again on any of our hosts. So we were able to do that. Like the rule took 15 minutes to push, and maybe the analysis took another like an hour or so. So within a few hours, we were able to make it so this malware would never be getting on our infra. That's another good use case we have is malware scanning. So we leverage multiple hooks at the same time. So in this case, would be like connect and also file close. So if a process connects to like the downloads, like has a certain size of packages and then downloads them, and also closes a file on the file system, we assume that this file that's closed is actually downloaded from the internet. So we can then trigger one of our responses to upload this file for scanning. Then after that, if that file has a malware, we do an alert, and we also prevent people from opening that file on the host. Now I wanted to talk about file lineage, which is the more involved file tracking we currently support. So the use case for this is we have a lot of files that are very protected, and that we don't want them to get stolen. So this is like LLMs, AI models, user data, et cetera, et cetera. So we use a variety of hooks to be able to track where these files come from, where they are moved across the file system, and if they're uploaded. So we usually, whenever a file is created, we tag it based on set of paths we already know, or the IP of origin. Like if you know that AI models are stored on a certain AWS bucket, whenever someone downloads from that bucket, we can flag that file, and then we can store its path in BPF, and then we hook to different file movements like copy, move, rename. So we make sure we can keep track of where that file is going. We also track every file that's derived from it. For example, if you have a process that opens the file of interest and then writes a file after that, we also track that file because it could be a file that's derived from the first one. For example, if you're compressing that file with tar, we will log any files that come out of that. And for example, with tar, we know that tar is this compression program by binary path, and so we can tag that file with compression or decompression. And for more complicated use cases, we just tag it with like direct file because we don't actually know what it is, but we know it might be important. Finally, we can do a similar thing where if someone opens the file and then talks to an online service with a like certain amount of bytes, certain like parameters, we can assume that it's operating the file somewhere. And then if that is the case, we can we take the whole lineage of that file and then we log it as an event for further processing. So how do we do that? We have the syscalls for move that actually covers both moves and rename. And then, like I said, we hook into file open and file close for copy, compression of the ref files. We also hook into the deletions. So if you delete a file, we make sure to like untag it because we want to save memory when we can. Obviously, we cannot track every single file, and whenever we have the option to like save a memory, we're gonna do that. So deletions deletes that record we have on our side. And then upload, we connect both into connect and file open. So in the chart I have here, you can see like process one might download the file from like a S3 bucket and create it. Then process two could copy or rename it into a separate file that we also track. And then process three could upload it. And then we can track the whole thing. So this is some pseudocode. I'm not going to go through it too much, but basically we check, like we're in the hook, we check that like the file path is correct, like the file, it originated from a file system we care about by type, and we can ignore all the temporary files in /proc, for example. And then we check if it's a file of interest, and then we just move from there and emit the signal, emit the event to user space. Similarly for delete, very similar checks. The difference is here we check that if the file is already tracked, right? If it's already tracked, then we care about removing it from our side. And in this case, we will create an event to user space. So after all these events, we get all these events from the BPF space, but then we need to track them, right? We need to make sure like we need to go from a create to a rename and have this like direct acyclic graph. And for that, we decided to use SQLite. I like SQLite. And the reason is because we don't want to store everything in memory because we were very memory constrained. So SQLite allows us to store everything on disk. And that would allow us to track more files and do more interesting stuff. And then after that, when we get an upload event, we can use a recursive query to traverse that graph. We usually just go like up, right? We go on, if we have upload, we just go up to compression to rename, and then when we get to the create event, we know that we have this whole lineage, and then we put it all in the log and we log it. Another cool thing we can do is that provided files are tagged up appropriately, we can track a file when it moves across computers, across hosts. So imagine I download a file on my computer, or like on my dev server, and then I download it to another host. Like I'll operate another host, and then I compress it and then put it on Google Drive, for example. Since since we detect the initial download event and then the upload event, and then download event on the other computer, we can have lineage across computers. So in this case, you would know that, okay, it started on host X and went to host Y, and then it ended up on Google Drive.
Can I ask a question? Like, what happens if there's like a, I don't know, let's say load balancer or like some NAT gateway in between? Like, how do you track that the original source was host X and not something else?
Could you repeat the question?
I mean, if there's like some middle box in between, right, which like nats the network packet or something, like how do you track that so that you also taint the application on host Y?
That's a good point. I guess in this case, we rely on other security practices, security things we have for that not to happen, like SSL certificates or like prevent someone from getting our infra completely. So no, we don't have the solution for that in this example, but we just hope that all other services like BPF Jailer or like cert certificates issuance will catch it.
Then when this gets received and then let's say on an application on host Y, so you basically also have to taint all open file descriptors, assuming that eventually some information could be written to those file descriptors, right? And then you also have to track those, or?
Yes, I mean currently we hook into file open and we just like catch every single syscall and then do our checks there. But yeah, we do have to do that.
But you have to do this even before this gets received, right?
Even before it gets received, yes.
Yeah.
Yes. Yeah. So some challenges we have, what we want to improve on. So a lot of our filtering, just like BPF jitter, rely on file path, which could be finicky. So we want to move to inodes eventually, which isn't completely trivial since it will change a lot of how we interface with these hooks. We are very memory and CPU bound, so we can track every file. So now, like, this forces us to be creative on how we want to tag these files because we cannot tag every single one. And currently, we support file path and IP addresses. We also want to move towards hashing these files of interest. And the reason is because it makes it easier to like know if a file is moving, like and know what have a signature of the file that's moving. Currently, we rely on like IDs we bake in into these files. Like the files are really important to us. We embed an ID into it, and then we use that for identification. But having hashes is obviously way better. The constraint here is that files could be really big, and that hashing everything could be very expensive. Currently, we lose state between restarts, so we don't like we also for the SQLite DB we also wipe it between restarts, and the reason is we don't want things to balloon out of proportion, and since we just released that system, we want to make sure it's stable enough to be able to maintain states. So currently we don't do that. And we want to obviously support better ways of tagging files. And yeah, we're still debating on which ways we want to go with that. But yeah, this is our last point. And yeah, that's all I had for you guys today. Does anyone have any questions?
What happens if you mmap a file, delete it, and then write a new file out from the mmap? Do you lose the tracking information?
Yes, you'll probably lose the tracking information in that case. And like if the file is like written back with a different file extension, like which is pretty trivial, then yeah, we will lose that tracking. There are a few edge cases we have currently, and this is one of them. Question in the back.
Okay, so I'm kind of curious about the consistency of the file tagging. So I understand the tags are kept in that SQLite database, right?
Yeah.
How does the tag move with the file in the system? As an example, say that I put it in a tar archive, right? So you multiplex multiple tags and files into a single file when you compress it, and then you extract it. So now, how do you choose which tag goes to which file out of the archive?
So a few things. So all the files that are tagged are all the file paths or files that are tagged are in BPF. So we have a map of everything that's tagged there. And then in your example, every single file that will be created from tarring and on-tarring will be tracked separately. And it will be one node in our SQLite graph.
Right, but you have an archive that is now mapped with multiple files, which with their own tags, right? So when you get the files out of the archive, how do you re-tag the created files that are just made now as the archiving?
How do we tag them? Because we know that the archive is tagged from because when we can go through it now. Like when you have the file that you compress into an archive, we tag the archive, and then when a process opens the archive and removes stuff from it, we tag all the files that are created from that because we know that the archive is tagged too. Hopefully that answers your question.
Right, but how do you recreate the mapping? Because, for example, I could put like files in the Targa archive, right? And then get it out with strip components up to the point where you can't recognize the file anymore. So is the tagging based on the file name, on the contents, or how do you remap the files getting out of the archive?
Yeah, it's based like it's based on the file path, like.
Okay, so you could like lose tagging if you do it this way.
Yeah, you could lose tagging.
Okay, so it's kind of heuristic based. It was what I was getting at. Okay.
Yeah.
All right, thank you.
So again, this is kind of like a philosophical question, but is the threat model that you have an AI agent that might be trying to exfiltrate data like on its own, like doing stuff like that?
In this case, file lineage is not only for that, but also for someone that might have malicious access to the computer. So it would do both. But yes, it is a potential attack vector that an AI model could do that. And I feel like it's going to be more and more prevalent. Like if you download a malware, like you can just talk to LLM and figure out what to do from there, right?
All right. Thank you very much.
Thank you, everyone.
So now we have a coffee break until 5.
I can probably put another laptop on the side.
I mean, for notes, yeah.
Okay,
Let me
perfect.
just put it here.
You are currently the only person in this conference.
No, it's good. Okay. Sorry.
No worries, yeah. Cool. Maybe just delete that, maybe?
I don't know what this even is. How do we get out? Delete?
Oh.
This one works. This one. I don't know.
I mean, it's okay if it's just on this first slide. Yeah. Okay. Okay. Hi everyone. Hopefully you can still see the title of this presentation. Yeah, I'm Justin from Meta. And I'm here to talk about two interesting problems that we've had to tackle with respect to file system enforcement and sort of the pattern matching system that we built for this in eBPF. So I work on both MetaArmor, so that's the EDR agent that Carl presented just now, as well as BPF Jailer, which is the mandatory access control solution, our internal solution that will be open sourced in 2026. That Liam presented just now. So you'll sort of see references to both of these services throughout this talk. And a lot of the work we're doing here is kind of motivated from problems that we had to address in kind of deploying these solutions. So yeah, we'll first start with some real world problems, some of the theoretical foundation we used, some of the BPF specific challenges we hit, and how we solved them. So let's start with the problem. I'm sure folks here have seen this in one flavor or another, but a strong theme of this year is sort of AI agents, right? And as the host infra security team at Meta, it is our job to prevent these agents from running rampant on our hosts. So we have a strong partnership with our internal red team, who we work with to iterate on exploits that they discover. And one of such risks they identified was the ability to impersonate and subsequently escalate their privilege by acquiring certs that they shouldn't have access to, right? And, these certs are effectively just files. Yeah, and here's what makes it really scary, right? With in addition to being able to exfiltrate a lot of proprietary data, having access to coding agents or AI agents essentially exacerbates this risk because you're now able to parallelize these exploits, right? So the problem that we set out to solve is how can we lock down all these access vectors and apply these security policies? And so this is kind of a BPF Jailer problem that we had to tackle this year. There are a lot of different ways you can access your host remotely, right? I'm just going to pick one example here to show with SSH and how we integrated with it. But at a very high level, right, when you SSH, you access your host. On the other end, we identify the the associated SSH session, and we enroll that into our protection. And once enrolled, all subsequent forks, all subsequent execs, from this original session will be part of the same protection. And once you're part of this protection, we prevent a bunch of things, right, including being able to say kill the BPF Jailer daemon. But what we're particularly concerned about here is the file system enforcements, right? Like we want to prevent it from accessing these certs. And the actual code for how to implement this is Liam presented earlier, right, with our finite state machine based file matching solution. And the user side is you specify these file paths that you want to protect, and we essentially prevent you from opening these files. But we quickly ran into one challenge, and there is sort of a limitation with how we do our finite state machine file matching, right? That's the whole diagram that Liam showed earlier. and that's the state is sort of immutable, right? Once you set up the entire finite state machine representation, right? But like you can sort of see how this can be a deal breaker when you're considering runtime context, right? So if specific things change throughout the lifetime of the BPF jugular daemon, we kind of want to be able to account for that. And in this specific case, right, users can access a host, they can move to different hosts, right? Certain hosts will be like reprovisioned, right? And so you can't really enumerate all the possible users that will have access to this host. And even if you could, right, this is not a solution that essentially scales, right? So the problem kind of boils down to how can we account for some type of runtime context in this FSM-based file matching. And so to support this, we added the notion of variables, right? And so it's essentially a two-phased approach. When you're loading your security policies, we have some specific notation to denote that this is a variable. This is not your typical file path. And we assign IDs accordingly. And when it comes to matching, right, at runtime, we follow the similar a method, right, where you extract string views of your directories and then you match them accordingly. But we have an additional setup where now not only are you looking up against these predefined nodes, you now also consider, is this a possible variable, right? And basically, the key takeaway here is that the variable names are compile time and the variable values are runtime, right? And so we have this kind of runtime context that you're now able to update dynamically. This like under the hood is basically just a BPF map, which you're able to change and mutate throughout the lifetime of the daemon's lifetime, the BPF jugular daemon's lifetime. And so what this gives us is the ability to customize our security policies with context. And we don't have to have like a whole list of policies or file paths for the specific use case. And it also extends beyond this use case, right? Because now you're also able to account for other runtime contexts like your container, your VS Code session, et cetera. And we don't have to do any type of like forking out to user space, have user space tell us something, and then like have your typical time of check, time of use exploit there, right? All the enforcement just happens with information that is already present in kernel space in your BPF program. But there are limitations, of course, right? And I think one key thing is expressivity, right? We realize that the fundamental basis of how we implemented this is we match based on each of the directories, right? But if you want to have say a UUID in this directory, right, and you want to allow it when it matches a specific format. So we have some examples on the screen. We can't really express that with our current approach. And so yeah, and in addition, there's also like your typical things which our service is primarily leveraged by security engineers, and they like regexes. So this kind of segues into our next topic of why can't we just run regexes in BPF? And you get a lot of good niceties with this too, right? In terms of like performance-wise, right? If you actually wanted to use a regex, currently you would probably have to log your information and then have user space deal with it, right? And so if you're able to have this expressed natively in the kernel, run in the kernel, then none of that has to exist. In addition, you also have your verifier guarantees, right? And we'll talk a little bit about that later. And we also thought a little bit about maybe doing like a more simplified version, like a glob-based approach. And I'm happy to talk more about this later, but the short answer is we essentially realized that if we were to do this more simplified approach, the work required to implement it would be very similar in terms of how we represent things and how we step through the actual simulation. So we just decided to opt in for whatever was more flexible and basically remove certain features in the entire regex feature set that we deemed either not necessary or too complicated to support. And we basically decided to support a limited set of features. And these are kind of also motivated by the security engineer partners that we worked with. Cool. So I'm going to go through a couple motivations just to set the tone, and then we'll talk about how we actually did this. So of course, performance, right? I mentioned earlier that I work on MetaArmor, and so one thing we realized is that we actually spend a lot of resource, a lot of CPU time in user space evaluating these regexes to essentially filter our logs, right? So a little bit of a briefer. MetaArmor collects security logs, and we kind of err on the side of caution where we collect as much telemetry as possible, but then we selectively filter away things we don't really care too much about, right? So that's the high-level idea. And how we decide what to filter away is based on our partnership with our security engineers, and they, sort of provide this to us in the form of regexes. And so this is kind of the how we landed in the status quo we have right now. And we realized some stats on the screen, but there's a lot of opportunity for this to be optimized away, right? Multiplied by the scale of our deployment, that's a lot of dollar signs. And another benefit is safety, right? There has been a couple production examples where poorly written regexes has led to actual production issues, right? In 2019, there was this issue with Cloudflare where they had a bunch of I believe it was 6 to 7 back references in your regex, leading to some essentially DDoSing your own regex engine. And another example is there on the screen. So safety is also important. And then finally, having this guarantee in BPF space allows you to leverage a bunch of the other existing BPF features, such as LSM hooks, and enables us to essentially do enforcement in user space and unlocks a lot of potential. Sorry, not user space, kernel space. And unlocks a lot of potential. So, a couple examples, right? Say you want to write a DNS parser, you're now able to make decision based on the content of the what you're trying to look up, essentially, right? And so perhaps someone tries to exploit this by including proprietary information into the actual subdomain that they're trying to look up. Well, now you can detect that, right? And more flexibility, we talked about that earlier. And the third point is something that we actually have worked on, where we are blocking agents from executing specific command lines. Currently, this is based on directly matching the actual arguments. But say we have access to regexes, we are now able to just essentially lift whatever user space specification we have and just directly apply this without having to do any type of context switching there. So it's great. But of course, there are challenges, right? You can't exactly just import RE2, right, in kernel space and just use it. And with a lot of this complex simulation, you also have to make sure that we're also operating within the restrictions, right? So you can't have unbounded loops, no dynamic memory allocation, etc. So here's the high-level idea of what we set out to do. And the key insight here is that regex expressions will all have a equivalent NFA. So NFA stands for a non-deterministic finite automata, and based on the paper linked on the screen. And there has been a lot of existing implementations where they leverage the theory here, constructor DFA, and then you have your user space regex engine. But the key challenge we solve here is, well, why can't we just represent this with eBPF, using the maps, and since you linearize this, right? So that's basically what we tried to do. In the user space stuff, this is pretty well defined, so I'll go through this pretty quickly. But the idea is you have your regex, you parse it, right? You create your AST, and then you convert that into your DFA. Then, in order to have a deterministic execution, right? Because with NFAs, you can enter multiple states, but with a DFA, you only have one. We convert this, right, to something that's deterministic. Finally, once you have something that's deterministic, you represent this with, as we'll see later, a couple one to three BPF maps. And then now you just have to step through this in a sort of intelligent way, and we'll see the restrictions we hit into pretty soon. And then you have your full engine. So I'll go through a quick example. Say you have this pretty simple regular expression. So you parse it, right? Nothing too special here. Here's just your recursive descent parser. And once you have your AST, you apply transformation. So essentially, you can convert each of the nodes in your AST to these fragments, which kind of represent how you would step through this logic in a NFA representation. And when you apply this to every single fragment in your AST, you get this. Oh, I forgot to step through the slide. Sorry. So these are the fragments. Yes, okay, now we're aligned. So when you step through your fragments, you apply the fragment conversion to all your AST nodes, you stitch them together. Now you get this on the right. And then this is your NFA. And then you apply some known conversion from NFA to DFA, basically called subset construction, and you have your DFA representation of the regex I had just now. One quick note, right? On the screen, you'll see that there's some of these loops from the state to itself, right? These we added just to support substring matching, and I'll talk a little bit about this later, but we eventually decided to not support substring matching due to the amount of states that it generates. But for this example, it will still be on the screen just for completeness, right? So it's possible to support substring matching too, but it just leads to some additional complexity, which we'll talk about later. Cool. So now I'll quickly talk about what from your if you were to write a BPF program, how you would use this, right? For how you would think about this. It's essentially a byte-by-byte simulation, right? Once you have your DFA, you can process your inputs byte by byte, and you essentially step through your DFA. And since we don't have the notion of a graph in BPF, we have to flatten this representation, right, with the existing BPF maps. So there are three that we use. One is that essentially contains pattern metadata, right? So this is not strictly needed. You could, and I think this is actually a good point for discussion later on. We could also flatten this so that all three maps are actually just one. So you can support nested maps, for example, right? So you can have a specific regex per, say, C group, right? Yeah, if you want to store anything more complex, then you probably don't want to pay the penalty of having too much complexity in your key. But anyways, I digress. So with your pattern map, you encode basic information like what the ID of this regex is, as well as any additional metadata you want in it. And this is kind of the crux of everything, right? You have your transition map, right? So on top right, we have the DFA that the example that we had earlier, and in the bottom right, we have sort of a snippet of what the map or the transition map would look like. You're essentially representing from state to, right, all the possible ways I can get to state. Sorry, all the characters that you could take as an input, and what it would mean, right? So if in this example, right, the majority of these are essentially to the actual self loop, right, which basically means, well, except for all these other characters, I'm just gonna go back to myself, right? But like it's a non-trivial, a trivial optimization would be just, you could have, say, like a dummy state, right, where you enter, and then that kind of represents all your self loops. So it's a simple optimization to make, but for the sake of demonstration, I'm just going to list out all the states explicitly. And yeah, so this is your transition state map. And then finally, basically once you enter an accept state, you want to now log specific information, right? So like, I've accepted this, and then if you want to, from the user's perspective, right? Like user as in I'm now using this regex engine. If you want to add any additional information about when I match the state, what to do, then you can also store this, right? And then, back to the point I mentioned earlier, the first and third map are technically could be included in the second one too. But, you sort of pay the penalty of having an expanded key or an expanded entry, right? Cool. And a couple more notes. We use a macro to just help streamline some of this. So on the left, this is sort of the macro. If you were to use this as a user in writing your BPF programs, this is sort of what you can kind of expect, right? You use the macro and expands into your maps necessary for the regex matching. And then in your actual code, right, we have a very simple LSM program here where you look at your file path, say you manage to extract your path here, and you match it. Using the prefix, we will expand this. We will expand this into the relevant maps, and you would call this BPF regex match function, which we'll see what it does later, and it will return you the number of matches based on the value. You can do specific things. So yeah, here's the sort of a abbreviated version of the code. Any point where I do abbreviation, I do put a comment on what I did abbreviate. So yeah, it's essentially 3 layers. So in the outer layer, we kind of set up some loop context, and we do some workarounds to prove that this is bounded. And then within the actual within this method, we use the context to do this bounded iteration. And then finally, in the actual content of the loop function, we do 3 things, right? First, we check if the current state is accepting, and then the way you do that is you look at your final states map, right? That kind of shows this is a state that we've entered if you're accepting. If you're not, then you do the transition, right? You look up into the second map and you see, given this current character, what state do I enter? And then if you hit a dead state or if you hit a final state, then you record that and then you return and you're done. Return in the sense that you populate it to the context and you return 1. But yeah. So yeah, that's the high level idea as well as the kind of abbreviated version of the code for how we do this matching. So now talk about some challenges. When it came to implementing this, we, sort of, as Liam mentioned, right, we sort of hit into every single bound that the verifier has to sort of provides. Actually, before we even get to that, right, combining these DFAs, let me take a step back. So it's useful if you are able to represent 1 regex, but it's much more practical if you want to have multiple, right? And when you want to combine multiple regexes into 1 DFA, it is sort of complex to make sure that you're able to share state correctly, but it's also essential that you do so, because if you don't do so, the number of states that you can represent in BPF space is very limited, right? So the high level idea is I want to simplify in user space the states that I have in the transitions as much as possible, such that when I load it into the actual BPF maps, I don't have to load as much information. And so that was sort of a big challenge that we had to wrestle with, and a lot of workarounds with respect to compacting certain states, as well as compacting certain transitions, right? So implementing these intermediary states and dummy nodes to represent this. And the second thing is, to also keep in mind that a lot of the use cases with, what we end up building here is I want to integrate this with an existing program, right? And the existing program sort of has conditional logic, has other things that it's doing, and the verifier limits apply to them too. So the challenge here is, not only do you want it to reduce the footprint of this to fit within the verifier limits, but you also want to reduce it in such a state that it is also usable by other programs. So yeah, we currently, these are some of the limitations that we do apply. As well as the feature set that we support in the top right. Yeah, a lot of these we are still working on, right? And from preliminary integration, this has shown quite a bit of performance improvement, though I wasn't able to get a demo program working in time to perf this. But a couple things on our roadmap, right? Plan to open source this in 2026, and as well as apply some of the mentioned optimizations that I talked about and how to compact the state. And one thing we are thinking about is how can we do all this representation in 1 map, such that you're now able, then you can support a bunch of other use cases with nested maps, right? And then able to have the different context per, say, C group, or per process. Yes. And I think that's my last slide. So yeah, stay tuned for where we go next. And thanks for coming. Happy to answer any questions.
Hey, this is interesting for me. I sort of went through this myself, I think, at one point. And I was thinking about where the limits are coming from for currently you said 64 states, I think.
Yeah. So let me just go back to the pseudocode. There are three types of limits, I think, off the top of my head. One, as you mentioned, is the number of states, right? Because the number of states determine the number of entries in your the transition map, right? And it's sort of like a multiplicative kind of thing, right? So, and the second thing is the number of characters too, right? So it's like the number of characters as well as the number of states you support kind of determines how many entries you have in your transition map. And when you have this in part of your program, you kind of need to show, well, do all these transitions the verifier will check, right, that all these transitions will lead to like a valid termination, and then that sort of increases the amount of instructions that it will have to check by like a whole lot, right? And so we constantly yeah.
Yeah, please.
Well, that's what I'm getting at,
Yes.
right? Like, so 64 states or even 8,000 states makes no sense, like, given that you use like BPF loop, or you could use like more modern BPF for loop, right? So if you are running into some like verifier limit instructions, that must be something else than just like number of states, right? Or like we can tweak your code to satisfy some like convergence conditions in the verifier, and you'll be able to do thousands of states. I think that shouldn't be a fundamental problem here.
So 64 states, are those DFA states?
Yes. So states are sort of like defined by us, like however we want, but basically the number of like we can say merge multiple DFA states into one if we realize that the possible transitions are all the same. So in terms of 64 states, that's just the number, like the actual this key, the state ID, basically.
That looks like DFA states to me.
Yes.
Okay. So normally, if you have 8 NFA, so 8 characters, right? If you have 8 characters of regex, you can easily go up to 64 states. Basically, that's your upper bound. So basically, you can then say, I'm supporting currently 8 characters, or do you have, like, are you guys checking for these? Like, have you tested for these? Like, are you looking to support more? And basically, I'm looking to just see how we can support more.
Yes, 100%. I think to Andrew's point too, right? I think we are definitely aggressively trying to make this actually useful, and so as you mentioned, right, supporting more than 64 states is going to be very important, because once you have regexes that aren't basically just like beyond the toy program, it is going to be like one of the restrictions that we run into immediately. So that's definitely something we're looking into. And I think one nice thing about the setup is that you can do your optimizations sort of in parallel, right? So in user space, you can be like, how can I represent this DFA in the most compact way possible? And when you actually do the loading, right, you can do some optimizations there to say merge a couple states into one, right? When you actually represent this in the transition maps. So that's sort of a long-winded answer, but yes, that is something we're looking into.
Perfect. Sorry for hogging. Just one more question. You said we cannot combine, or I don't know if the cannot is the exact word you use, but you don't combine currently multiple regexes. Why isn't it's an OR operator? Like it's not an operator.
Oh, we do combine.
Okay.
Yeah.
Okay.
Sorry, I might have misphrased. Yeah.
Oh, are you using shunting yard to come up with the NFA? Are you using shunting yard algorithm to come up with the NFA? Probably. Or are you just also? I didn't see that you mentioned that how you come up with the DFA image? Is this like a custom process that you go through to come up with the NFA first?
We use like Thompson's construction.
Yeah, Thompson.
Yes.
Thank you.
Mm-hmm.
One more question. Why packed? Why attribute packed?
I'm sorry?
Why attribute packed? On the
Wait. Sorry, I didn't quite catch the question. Why? What, sorry? Oh, Liam, would you like to?
bad habit. Yeah, bad habit. Yeah, but this state ID will be byte by byte. So like when you compare in state ID, it will be like giant if. And probably without BPF loop, just BPF4.
Mostly have it, but also I wasn't sure.
Mm-hmm. Yeah, and also just to add on, MetaArmor supports, I guess this is sort of internal, but like MetaArmor supports older kernel versions than BPF Jailer. So if we want to also use it in MetaArmor, we do kind of want to, I think we support back to like 5.19, right, for MetaArmor, yeah.
Yeah, well, when you go into open source, use the modern technique, like BPF4 or whatever, may go to, and then like whole state machine will be like fit on a slide. Currently, you cannot because of you have to create this giant context, pass it into loop in a callback, then it will fit in a slide, like guaranteed. Because like DFA state machine is just like this, next. It's like loop will fit on a slide.
Yeah, excited. Maybe next year we can present it again with one slide.
But yeah, it's good. And have you considered what grep is doing with the lazy DFA?
I'm not aware of that, but happy to look that up. Yeah.
grep. So the problem with like projects that like DFA can also be gigantic, but it doesn't have to be full NFA to DFA conversion. All this like the DFA optimization, this is my practice. I don't think it was that successful, but maybe you will be lucky, especially since you have a limited regex. But grep is doing, the way grep works is doing this lazy DFA. It constructs it when it's necessary, like when, so it doesn't do the whole, like, because NFA to DFA can also like memory explode. In this case, of course, it makes sense to do the whole like DFA up front, since then you like put it in a map and then everything you're ready, you don't think about it. But if you have indeed like gigantic number of like regexes, you would have to use something like lazy construction of the DFA, and you can like shell it to whatever user space and potentially, I don't know, just a thought.
Interesting. Yeah, we'll definitely. Look at that.
And what do you do for, since you're doing like regex, like for regexes, do you do like string match? String match as well? String search?
Like you mean extracting, right? Specific things from the regex?
String search. Like if you have whatever, like if you have, I don't know, 10,000 rules and most of them are strings, then there are like algorithms to do like string search. No, it will be different algorithm, but like conceptually, since you do this, like construct whatever in user space and walk the table in kernel, then all the other algorithms are on the table, like Aho-Karasik, the one that's like very fast and efficient would be to use it if you need to do the string search.
Interesting. Yeah, I think I'm not aware of a use case for that, but that would also be very interesting to look at. Yeah. Okay, sorry. Yeah. Thank you.
For coming. Yeah, grab your browser. Speak out.
So you can switch
Are you
here
guys-
and the other thing we discussed with the video. Yeah. Okay, perfect.
Hello, everyone. My name is Hemant. I work for Microsoft on the Azure Container Networking team. So we provide, if you use Azure's managed Kubernetes service, you'll have to select a container networking plugin for it. And we have an offering called Azure Managed Cilium. So today I'll be talking about implementing in-kernel FQDN policies with Cilium and eBPF. So 2FQDN policies are one of the Cilium's most popular features. Users love to use FQDN policies because it's very simple to write them. You can just say, okay, I want to allow traffic to the following bucket on S3, write a policy, and that's it. And it also has decentralized policy enforcement compared to having centralized proxies sitting somewhere on the edge, sending all the traffic through those proxies. In this case, it's actually decentralized, so that's good. So here's the agenda I have for the next 30 minutes. First of all, why do we want to do this? DNS is hard. BPF is writing DNS in BPF is hard, so why combine two hard problems? But to understand that a little bit more, we need to understand a little bit about how Cilium implements the current 2FQDN policies. So there's a user space proxy that intercepts all the DNS traffic and enforces the policy. There are some limitations to this because it's in user space, and we'll look into what those limitations are. And some of the attempts to fix those limitations in user space. And then we'll go into what it takes to actually implement this whole thing using BPF inline in the kernel. For that, we'll need to take a closer look at the DNS RFC itself to understand how the protocol looks like and how we should write a parser. And it's actually pretty common in Kubernetes for DNS responses to be a lot bigger. So services tend to be very large. So you might have too many IPs. And when that happens, UDP may not be enough. So in that case, DNS servers tend to set a truncation bit that will force the clients to make a DNS request over TCP. So in order for the system to actually work in all cases, we need to also do support DNS over TCP. So I'll talk about what it takes to implement stream parsing for TCP and some of the next steps. So just a quick refresher on how Cilium actually implements this. This is how Cilium's 2FQDN network policy looks like. In Kubernetes, most things work based on labels. So your workloads say, these are my labels, and then your policies can select those labels and say, this is the policy I want to apply for those endpoints. So here I'm basically saying that for endpoints that have org empire and class mediabot, enforce this policy and allow traffic only to api.github.com. And you can also say which specific DNS server you want to allow traffic to. And another interesting thing that's worth noting here for Cilium's implementation of network policies is Cilium enforces, at least Cilium represents the policy in terms of identities. So let's say you have a deployment with 5 replicas, and all those 5 replicas have distinct IP addresses, but Cilium only has a single identity. So any group of pods, which is a deployment with a unique set of labels, gets just one identity. And that allows us to deal with the pod churn. So basically, Cilium has a daemon set called Cilium Agent that runs on every single node in your cluster. And its whole responsibility is to distill this policy and push it down to a BPF map. And effectively, what that BPF map is going to look like is your local identity, that is the pod's identity, and what are the other peer identities that workload is allowed to talk to. So the user space computes this policy and puts it down to the BPF map, and then there are a bunch of BPF programs that look up that BPF map to decide whether the traffic is allowed or not. So right now in the FQDN subsystem, as I mentioned, there is a user space proxy that intercepts all the traffic. So let's say you have a pod, you're trying to make a DNS request, and if you have an FQDN policy, there are a bunch of redirection rules that are placed in that redirects the traffic to a user space DNS proxy, which intercepts it, makes a request to the upstream DNS server. Once it gets the response back, it sends the mappings to Cilium agent. Cilium agent will then take the IP addresses and allocate the identity for it and update the policy map, right? You can see this is quite involved and there are a bunch of challenges with this. So the DNS proxy is built into Cilium agent's user space daemon. So if your agent goes down because you're rolling it out or patching something, then your DNS proxy also goes down with it. And what that means is, and these redirects are unconditional, so your DNS traffic will be black hole. And there are also limitations on how many concurrent requests you can handle in this DNS proxy. So you'll have to constantly tune them based on what your workloads are doing at any given point in time. So we have been trying to improve this user space model by introducing a HA mode where you have another DNS proxy that's running alongside Cilium agent, and then we kind of load balance traffic between them. But this also gets complicated because now you need to have an API between the out-of-process DNS proxy and in-process DNS proxy and exchange some policy information and do all of that. So we were wondering why not natively do this in BPF. So when I spoke to a bunch of networking people and asked them, should we do this? They were like, are you crazy? Why do you want to do that? But when I spoke to some security folks, they were kind of a little bit more positive. And thanks to Mahe for, somewhere here, yeah, for planting the seed that something like this is possible. So if you were to try and write this parser in BPF for DNS, there are a bunch of challenges we'll have to deal with. First of all, the DNS messages are kind of dynamic, so you'll not know ahead of time how many answers are there in the DNS message. So your parsers need to handle for that. And there's something called as label compression. Because it's primarily a UDP-based protocol, if you see an existing label, there would simply be a pointer to reference an existing string that we've seen in the past. And because it's in Kubernetes, DNS over TCP is also a possibility. So we'll need to somehow do this whole thing in TCP as well. And one of the other challenges we had was, remember I was talking about identities, and Cilium used to allocate these identities from the user space. Luckily, that changed recently, and we were pre-allocating identities, and this actually allowed me to implement this whole system because identities are already present for a given DNS name if you write the policy. All right, so bear with me for 5 minutes. We'll take a quick detour into RFC 1035 to understand how the DNS protocol itself is and how the messages are structured. And this is the high-level format of how a DNS message looks like. So you have a header, question, answer. These are the three components that we care about for this. And this is the exploded view of the DNS header itself, and it gives you some metadata about how many questions are there, how many answers are there. This specific field on QD count is interesting. We'll talk a little bit more about it. And then this is the exploded view of the DNS question section. The questions are called Q names. And Q names can be a little bit dynamic. So the way it works is, let's say if you have api.github.com, you would have 3 that kind of indicates how long API is. And then you would have however long GitHub is, and then GitHub, and then the length of com and com. So we'll have to parse these based on the length until you hit 0. And resource records are basically what give you the actual DNS answers. So it can be IPv4 or v6. Do I have this? Okay. Yeah. So if you look at the name section here in the resource records, so this is a repetition. So when you request a DNS name, let's say github.com, the response will also have a name section, which will also say github.com. But we also have a question section previously in the DNS message. So what DNS servers do is they simply have a pointer pointing to the name in the previous question section. And this is how the pointers look like. So if the first 2 bits are set, you know that it's a pointer, and you get to know what the offset is, and you have to go and parse that offset. In terms of actually getting the answers, there's something called RD length, which tells you how long the R data field is. That'll tell you whether it's either an IPv4 answer or a v6 answer, and we can go and get the answers. All right. So in terms of handling the dynamic part of the DNS wire format, the first thing to worry about is the QD count. And I was trying to make a DNS request using dig with multiple questions, and I could not. And turns out dig doesn't support it. So I was like, why is that? Turns out there's actually the problem with RFCs that are written in 80s is that they're kind of a little bit optimistic on how many questions can be supported by the RFC. And there's a follow-up RFC that tells you that the QD count is actually almost always just 1. So we don't have to worry about parsing multiple questions in the QName. It's always 1. But we do need to solve for multiple answers. And I don't have to explain this for this audience, but from 517 and above, it's easier to use BPF loops to write complex loop logic. So that's what I was able to use, and thanks to Dylan for excellent docs on this. Yeah. So we were able to use BPF loops to actually parse multiple answers and get them. But the thing that there's this one single bit called TC that kind of complicated my life for like a few months. This is the UDP truncation part that I was talking about earlier. And when this is set, your clients are forced to make a request again over TCP. So turns out we actually have SKSKB BPF programs with a few attached types called stream parser and stream verdict, which lets you parse TCP streams. And I was able to use SKSKB and SOCOPS to put up a system together that will allow me to do TCP stream parsing. So, I have a SOCOPS BPF program in combination with a sock map to collect the sockets. And then we have a stream parser program that kind of parses so the DNS over TCP protocol says that the first 2 bytes tell you how long the entire DNS message length will be. And the stream parser BPF program would basically parse those first 2 bytes and tell the kernel how long that message should be. And the stream verdict would be called once that message is available. So this is just an image to explain the whole system. So on connection establishment, we have a SOCOPS BPF program that writes a reference to these sockets into a sock map. And on the sock map, we have SKSKB BPF programs using 2 different attached types. The first one is stream parser and stream verdict. And all stream parser does is just read the first 2 bytes and gets the length of the entire DNS message. And then the stream verdict program does the rest of the heavy lifting. And for UDP, we have a simple TC classifier BPF program, and the DNS parser is actually shared between both of these systems. And one thing I did not have here is identities for DNS names. That, as I said, they're already pre-allocated. So if you have a policy that says allow traffic to api.github.com, the identity for api.github.com is already allocated by user space. I simply replicate that into the kernel space into a BPF map. And once I get the IP addresses, I look up what the identity for that IP should be and update the Cilium's policy map, endpoint policy map, so that the traffic is allowed. All right. So in terms of the first, this is not really a challenge, mostly because I did not know that I'll have to deal with nonlinear SKB data. So my read of the contract between stream parser and stream verdict BPF programs was that if the stream parser responds back saying this is how long my message is, then the stream verdict would have access to that. And I was running into a few scenarios where my verdict program would just not have any fields populated. And turns out we can actually run BPF SKB pull data to linearize that. I'm not sure if the UX could be better for this, but I spent a few weeks trying to trace the whole thing to finally discover that I just needed to run SKB pull data. And the next challenge is match patterns. So Cilium supports a very small subset of glob strings. So we only either care about star dot something or star dot something. So that lets you allow like a bunch of subdomains. So we wanted to just support that subset, or maybe like once just an open sources stuff, like we could use that. But right now, the current approach is we have an LPM try map with the reversed strings stored in a map, and we simply query that LPM try to see if there are matches. And if there is a match, then we basically strip off all of the stars from the policy and put it into a map. And on runtime, we parse the queue name and look up against the map. And if there's a match, we simply have to check how many dots are present in the non-matched part. So CNAMEs can get tricky. Basically, you'll have to keep chasing CNAMEs. Luckily, like Cilium's 2FQDN today does not support writing policies using CNAME. So you'll have to actually specify the leaf level domain name that you want to allow traffic to. So this part I did not actually implement, but it should be possible. I did run into a bunch of issues while trying to use BPF loops and data end pointers. But as I hacked on it, like it kind of fixed itself, and it was working on some kernel versions, but it did not work on some kernel versions. I did not have enough time to like go and bisect it. I have a quick demo I can show the whole thing. The window on the top left basically is just showing like my client part, which is called NetTools. And this is the network policy that kind of says for app NetTools, allow traffic to Microsoft.com and API.github.com. On the window below that, I'm executing into the Cilium agent, and it shows SKSKB BPF programs with attached type stream parser and stream verdict. And I have two of them here because I'm running something called kind, where it's Kubernetes and Docker. So both nodes are on the same physical node. So you see two of each of them. And this is the LPM try map that stores the mapping between DNS names and the corresponding identity. On the top right, I'm tracing the trace log. And once you make a request to Microsoft.com, it works. You can see some metadata about while this whole parsing is happening. And Cilium uses something called as IP cache, where it stores a mapping between an IP address and the identity. So all we need to do is update the IP cache, and the rest of the policy will simply go through. And after this, I also have a small section that demos the TCP part, but the demo is pretty much the same after that. All right. How do I stop the share? Yeah. Okay. Yeah. Thank you. In terms of next steps, garbage collection is one major challenge. So the most common use case people use FQDN policies is for something like S3. And when you write a policy like this on S3, S3 has a huge set of endpoints and clients constantly cycle through them. So you can end up having a lot of IPs in your BPF map. So it's important that we garbage collect them. So today, Cilium does this garbage collection in user space. So I'm relying on the same user space garbage collection, but for it to be completely user space free, like maybe we'll have to do garbage collection in BPF. I'm not sure yet. Proxyless DNS visibility. So the neat side benefit for this whole effort is that while we're enforcing, in order to enforce policies, we're parsing DNS. So Cilium also has something called as Hubble, which lets you get telemetry on what your applications are doing. And today, like we require users to write these policies called visibility policies, and it redirects all the traffic through a user space proxy just because they want to see visibility. But with this, you can have proxyless DNS visibility. I haven't gotten around to doing like exhaustive performance tests yet. This was mostly an effort to see if this whole system works end to end. And DNS also has DNS over HTTPS and DNS over TLS. Not sure how they're going to work. And for regex support, once Meta open sources that, maybe we could try that and make the whole pattern matching a little more robust. Yeah, that's pretty much what I have. Any questions?
In your current implementation, so when there are like patterns that you want to match, which do not fit into this LPM thing, you still have to use the fallback user space proxy, right?
Yeah. Mm-hmm. Yeah. So right now, I think the only use case that is not supported according to Cilium spec is if you have wildcard like star somewhere in the middle of a name. That's the only thing that the system doesn't support. But other than that, in practice, most people just write like star.api.star.github.com or something like that. So for most cases, this should work. There is another approach where we split a given pattern into labels. Let's say store com in like first position, you have map for each position. And then you look up for each label. That gives you an option to like do specific handling for star, even if it's somewhere in the middle of a label. So it's possible, but it requires a lot more lookups.
And then the UDP-based implementation is based on TC, or okay?
Yeah, it's just I just call the same parser from Cilium's existing TC programs. And in terms of the SKB pull, like, is there something that we could do that will make it easier for newbies to do this? So basically, my question was if the first stream parser kind of tells the kernel how long the message is and how much we care about. And the users might always have to run skb pull for that amount of length. Yeah, anyway, this is probably a better question for the mailing list, but yeah.
Yeah, or maybe like a documentation
Yeah.
example or something. Because like sockmap's not really well documented at the moment, probably.
Yeah, if this was documentary, it would have saved me a bunch of time.
All right, thank you very much.
Cool. Thank you.
Do you want to present from your laptop completely, or?
No, I think it's fine. What would be the difference? Or how do you actually operate this?
So you have to go here.
Oh, just like,
yeah.
Do you see the screen? Okay.
Okay. And then if you want to share your screen, you basically.
So then, like after during live demo, I'll just share the screen. I will click here and just switch here.
Okay.
So I have this open. It's already.
Okay. Good. Then you have to take presenter from here.
Take presenter, but yeah.
Yeah.
I'll do this later. Well, okay. I think it's fine. Yeah, it's
just the mic. It's on. Yeah. Good.
Okay, I think we can start. So it's the last presentation for today, and it's actually have some same topic and similar, basically similar topic about DNS, and I think there is some intersection with the previous talk, so we can actually skip some part of like details about the DNS itself. But we will also do some live presentation. I think we found a way how to run it. So I will actually show you how it works on an actual machine. So this topic gonna be about the simple DNS server implementation with BPF. I'm working at Meta as a software engineer, and Martin from Meta also helped me with this talk with some debugging and advice around this. So let's start. So at Meta, we actually use a lot of different use cases for BPF. That's what Meta made our internal AI generated. What's the known use cases for BPF? I think it's pretty much everything for BPF. But also one additional use case we can cover here is BPF can also act as a simple server for certain protocols. So it's not a replacement for like a full-featured user space servers, but it can be excellent use case for a stateless server and some like quick packet manipulation. And actually, it can reply to the packets without any socket or any user process listening on those packets. So what would be the good use case for this experiment? It's DNS. DNS, originally it's a UDP-based protocol, And DNS requests are stateless and single packet requests. And response is also a single packet UDP data. So in this case, there is some overhead. I think like this exact picture was used in the previous presentation. So this is the usual structure of DNS request. So in this talk, we will focus on just first 3 sections. So yeah, we will not cover like authority or like additional sections. So just a simple pure DNS use case. So this is the more detailed view on a header, the first part of DNS packet. So here we have question count and answer count, and also the flag that indicates that it's a, I think it's a question query in this case. Yeah, one field that specifies whether message is a query, which is highlighted QR. So we need to care about those specific fields in the packet to understand if it's the query. So in this case, the query count is going to be more than 0. And as we learned in the previous talk, it's usually just a 1 query per packet. So an answer count is actually something that DNS reply with. So it indicates how many answers it sent back. So in this case, it can be bigger than 1. So some DNS names can resolve to multiple IP addresses. And in this case, it's going to be equal to number of IP addresses. Also, one interesting part is actual DNS name and how it's stored in the packet. There is no way to tell in advance how long the DNS name in the query. So we actually have to sort of dynamically parse it. And the format of DNS name, it also was covered in the previous talk, but just quickly show an example. So we have this first byte indicating the size of the subdomain name, and it like goes for multiple subdomains until it ends with 0. And then there is also the type and the class. So so in this case, what programs can we use to actually intercept and reply back? So C group type programs are not applicable in this case, because at this point the routing decision is already made, and we also have a very limited scope of changing the packet structure itself. At the same time, we can do this with TC and XDP programs. So later during the live demo, I will show actual example with TC and also XDP. And also, so for TCP, the main idea of this DNS server's BPF is that once the packet is processed and updated and answer is added to the packet, we reply back with BPF redirect and inverse the direction of the packet. So this way, packet comes back to the network stack as a response, and some sort of can trick the whole system thinking that it's actually the response packet that it needs to route it back. And the same idea with XDP, we can return type XDP-TX, and this will put packet back as the response. So what do we need to do? What sort of modifications for the packet? So we need to swap source and destination, IP addresses and ports. Also create an answer section with actual IP address, or like multiple answer sections, basically one per each IP address. Also change the packet size. And probably the most complicated part was the calculate the new checksum of the packet, and then the flip direction for TC or XDP. So for switching the source and destination, we need to update certain things. We need to swap MAC address on the packet, also swap source and destination IP fields in IPv or IPv6 header, and then also swap ports in UDP packet itself. Then speaking about the answer itself. So yeah, also was covered a little bit in the previous talk about IPv4 or IPv6 addresses. So there is a different type and different RD lengths and RD data for IPv4 and IPv6 in the answer. So it also might be different type. And it's based on the type of the original query. Is it 4A or just A for IPv4? So then also another step is to update the packet size. So we need to calculate the whole length of the new answers, and basically just adjust SKB or XDP packet and set it in UDP packet length. So, and for the checksum, the main complication comes from the DNS name itself. It might be various lengths that we need to learn dynamically. And also, if we want to create an answer with BPF, we need to use the same DNS name for sort of like lookup in BPF map. So in some sense, we need to, and also one requirement for the checksum itself, it have to be aligned. In some versions of kernel, it have to be aligned by 4 bytes. I think in newer versions, just by 2 bytes. So yeah, we need to kind of combine this DNS name and answers together, and then also add some padding in case it's odd or even. So to store like DNS records, it's just one example that worked for this experiment. I think, yeah, it might be also multiple BPF maps, or as the previous talk also mentioned, we can use LPM try and just, but we need to invert the DNS names because they kind of sort of like in the original packet, they go backwards. So, and then we can search for actual records in BPF map. So how can we actually use the DNS BPF? So there are several applications, at least some of them we come up at the company as potentially like useful in future. So one of them is alternative for its host file. Also like resolving the local queries. So it helped to bridge some gap between open source projects and like internal meta infrastructure, in the sense that we can still use DNS to do resolution, and we can kind of like dynamically place it inside like some containers. And also one of the possible use cases is resolving external DNS queries for as a DNS DDoS protection. Just from the sense that like implementation with XDP can reply faster and can use as a sort of this protection. So taking a look at every possible use case. So like for this talk, we have implementation of XDP and also TC BPF program that can reply to BPF queries. So to resolve external queries, we can use XDP program. So in this case, we don't need to run any like local user space server. And yeah, at the same time, only like simple use cases can be supported, like no like DNS over TLS or other more complicated. And also like no TCP support at this point, but yeah, it's probably still be possible to implement. And yeah, there is also some benefit with performance, just because, yeah, we don't need to go to the user space to resolve the packet, and we can reply it from the XDP itself. So the same for resolving the local queries. In this case, we can use TC program as an example. And so yeah, we don't need to override resolve conf. Like if you want to run some local DNS proxy, it's more complicated to actually like also replace resolve conf with this address to this local proxy and like do all the modification and then run the local server. So in this case, we can just replace this whole infra with just a BPF program. And also it shows some better performance for the same reason that it just doesn't go to like user space or to any like program to do DNS resolution. Yeah, and as the last option, it also can be replacement for shost files. It's very limited but easy option. I mean, in general, the hosts file, we can kind of just dump like the list of hosts and don't worry about it. But at the same time, there are some limitations for the host file, like it doesn't support multiple IP addresses. And yeah, it's also just a plain structure, which shows some performance degradation when there is like a huge list of hosts. So like it's also has a limited or some limitations. So in this case, BPF can be a good replacement or good option because it also only cover like some simple use cases for the local either testing or the local like proxy. Okay, so yeah, I will try to show the live demo. You just need a couple minutes to take over the screen. Okay, so yeah, my server just died today once, so hopefully it's gonna survive this live demo. So yeah, it's actually on the left side you can see. Oh, on the left side is one like big server, and then on the right side a small server. It's just to show them like external resolution for XDP program. So we will attach two programs. First, we can try TC program. So in this case, I'm running DNS loader, which is attaching TCX BPF program. And it's going to use this list of hosts as an input. So to show you the hosts. All right, so it's just 5 host names, with some of them with multiple IP addresses, and it's either like it's IPv4 and IPv6 addresses. So it's just a fun like Facebook, Amazon, Apple, Netflix, and Google host names. So first we can start TC program. So it will show if it resolve any of the like v4 means A or v6 for A hosts. So then we can try some local resolution with so in this case, it's just using dig to do some query for Facebook. Okay, let's run and hopefully it's gonna work. Yeah, so it shows some warning, which is sort of like under debugging at this point. But yeah, at the same time, it's able to resolve the AAA host. We can also try other hosts. Yeah, so in this case, it returned like 2 IP addresses. So yeah, we can also see those registered on the BPF side. If I stop the program itself, yeah. So I think, yeah, at least for Facebook, or if we try to do the same without the BPF program running, it's gonna probably just, yeah, there is no communication. Okay, so another experiment is with XDP. So in this case, we are attaching XDP BPF program with the same host file, and then trying to resolve host name from another server. And so this server is, so it's using dig and it's pointing to a small server, so to our server for the resolution. Yeah, and also, okay, there is also the perf. So DNS perf is the tool I also used on the slides. Yeah, so it ran through, I think, the whole list twice for the DNS names and resolve them. So there is a little higher latency than anticipated, but that's because those are like running across different regions. But overall, it's definitely like improvement for the latency. Okay, any questions?
Any questions or comments?
So how would you rate your experience, your development experience with, you know, the BPF tool chain and you know, my understanding is that BPF programs are written in sort of like a subset of C. How was that experience? I'm new to this, so I want to know what how you would compare it to, you know, other development experience.
I see. I think, yeah, there is some bar with the verifier. Yeah, it like you have to know, or you have to adjust the code sometimes to satisfy the verifier and run successfully. But usually it's a type of programs that's dynamic. So in this case, like the painful point was like DNS names, which can be like different lengths. So we have to dynamically parse it. But overall, I think the BPF toolchain is pretty nice, and pretty solid, and it's easy to experiment, and it's like easy to develop.
Thank you.
Do you also support DNS 4.6 and 6.4, or do you plan to support it? Or
DNS 4.6, maybe eventually. Yeah, right now it's a simple use case. So we can reply to IPv4, IPv6 queries, and also support multiple names.
All right, thank you very much. So this concludes today. And there's an evening event, so you can see this on your badge on the back side. It's a 13-minute walk from here. Yeah, see you all there, and then tomorrow, the second day. Suddenly adopted. To be a fan.